There is something around you right now that you will never see. It has no color, no texture, no sound. And yet, it is as fundamental to your world as the ground beneath your feet. It is a presence, an invisible architecture that quietly protects all of life from the background energy of the cosmos. Most of us live our entire lives without noticing it, unaware of the immense, slow-moving processes happening deep inside the Earth and far out into space. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This is the story of that presence, Earth's magnetic field. It is written into the memory of ancient rocks, the flight paths of birds, and the silent, dancing lights that appear near the poles. If you have ever used a compass, you have seen a faint acknowledgement of this field. That small, twitching needle is not pointing to a place. It is sensing a force. It is feeling the outermost whispers of a planetary scale engine, one that makes the world habitable. Understanding it is to understand how interconnected and how fortunate our existence truly is. To understand the magnetic field, it helps to first understand the space it protects us from. The solar system is not empty. Our own star, the Sun, constantly releases a stream of charged particles into space, a flow of superheated plasma called the solar wind. If it were to reach an unprotected planet, it would act like a slow, persistent sandblaster, gradually stripping away its atmosphere over millions of years. Eventually, oceans would disappear into space, and the surface would be exposed to intense radiation. We do not have to imagine what this looks like. We can see it in our own solar system. Mars was once a warmer and wetter world. But it is smaller than Earth, and its core cooled and solidified long ago. Its magnetic field faded. Without that shield, the solar wind stripped the Martian atmosphere away. Today, Mars is a cold, dry world with an atmosphere less than 1% as thick as Earth's. Its surface is a quiet reminder of what happens when a planet loses its protection. Earth's story is different. Our planet is wrapped in a magnetic field that extends far out into space, creating a region known as the magnetosphere. It is not a simple bubble. It is a dynamic structure, compressed on the side facing the Sun and stretched out into a long tail on the night side. This field diverts most of the solar wind around our planet, like a stone diverting water in a stream. It is our planet's shield, and without it, life on Earth would likely never have had the chance to begin. But the shield does not block everything. Some particles from the solar wind are captured and funneled down along magnetic field lines toward the poles. It is there, in the upper atmosphere, that the invisible field finally reveals itself. When these captured particles collide with oxygen and nitrogen atoms, they transfer their energy, causing the atmospheric gases to glow. The result is the aurora borealis in the north and the aurora australis in the south. These shimmering curtains of light are the visible trace of this constant, silent interaction. They are a sign that the shield is holding. So where does this planetary field come from? It is not created by a solid magnet buried in the Earth. Its source is deeper, more chaotic, and constantly in motion. It is born nearly 3,000 kilometers beneath our feet, in the planet's core. Our planet is made of layers. We live on the thin, solid crust. Below that is the mantle. And at the center is the core, made of two parts. The inner core is a solid sphere of iron and nickel, as hot as the surface of the Sun. Surrounding it is the outer core, a vast ocean of liquid iron and nickel. This churning, molten ocean is the engine that generates our magnetic field. The process is known as the geodynamo, and it relies on three things. First, it needs a fluid that conducts electricity, which the molten iron of the outer core does very well. Second, it needs energy to make that fluid move. Heat flowing out from the solid inner core drives massive convection currents, causing hotter liquid metal to rise and cooler liquid metal to sink, like water boiling in a pot, but on a planetary scale. The third ingredient is rotation. The spinning of the Earth twists these rising and falling currents into vast, spiraling columns. As this conductive fluid moves and swirls, its motion generates electrical currents. And where there is an electrical current, there is a magnetic field. This creates a self-sustaining loop. The electrical currents generate a magnetic field, and the motion of the fluid through that magnetic field generates more electrical currents, which in turn strengthen the field. It is an engine that has been running for billions of years. The faint tremor of a compass needle is the final, delicate expression of this powerful, superheated ocean churning deep within the Earth. The magnetic field is not just a distant shield. Its influence is woven quietly into the world around us. Modern life has, in many ways, become dependent on it. If you have ever used GPS, you have relied on it. While GPS works by receiving signals from satellites, those satellites need to know their own precise orientation in space. They use instruments called magnetometers to constantly measure the Earth's magnetic field, comparing the readings to a detailed global map of the field. This allows them to make tiny corrections, ensuring the navigation we rely on remains accurate. It is a silent partnership between satellite and planet. Our global power grid is also connected to this field. A severe disturbance in the magnetic field, caused by a powerful solar storm, can create uncontrolled electrical currents in the long wires of our power lines. This is not a theoretical problem. In 1989, a geomagnetic storm caused the entire power grid of Quebec, Canada, to fail in less than 2 minutes, leaving millions of people without power for 9 hours. An even larger event, like the one that occurred in 1859, could cause damage on a much wider scale. During that storm, telegraph systems failed across the world, with some operators receiving electric shocks from their equipment. There are also areas where the shield is naturally weaker. Over the South Atlantic and South America, there is a large and growing region known as the South Atlantic Anomaly. Here, the field's intensity is lower, and the radiation belts dip closer to the surface. Satellites passing through this zone are exposed to more high-energy particles, which can disrupt their electronics. The Hubble Space Telescope pauses its observations when it travels through this region. Data shows the anomaly is expanding and deepening, a sign of the complex processes happening in the core below. The field's influence extends even into biology. For a long time, it was a mystery how some animals performed incredible feats of navigation. How does an Arctic tern fly from the Arctic to the Antarctic and back again, over thousands of miles of open ocean? How does a sea turtle return to the same beach where it was born? For many species, the answer appears to be an internal, biological compass. They possess a sense called magnetoreception. They can feel the Earth's magnetic field. Birds are thought to have a protein in their eyes that allows them to see the magnetic field lines as a visual pattern. Sea turtles are believed to use both the strength and the angle of the field, not just as a compass, but as a kind of map, allowing them to sense their approximate location on the globe. Life on Earth did not just evolve on a planet with a magnetic field, it evolved with it. The field is part of the environment, a source of information that life has been using for hundreds of millions of years. We tend to think of our world as solid and its properties as unchanging. But the magnetic field tells a different story. It is not static. It is a restless entity, born from a chaotic core, and it is always shifting. The magnetic North Pole, the point a compass needle seeks, is not fixed. For over a century after it was first located in the Canadian Arctic, it moved at a slow pace of about 10 kilometers per year. But around the 1990s, it began to accelerate. Its journey toward Siberia picked up speed, reaching a pace of nearly 60 kilometers per year. This rapid movement became a navigational problem, forcing scientists to issue an emergency update to the World Magnetic Model in 2019 to ensure accuracy. While its pace has eased slightly in the last few years, its journey remains faster than at any point in recorded history. At the same time, the entire field has been weakening. Globally, its strength has decreased by about 9% over the last 2 centuries. This weakening is most dramatic in the South Atlantic Anomaly, the weak spot stretching from South America to Africa, which continues to grow. This leads to an unsettling question. What happens next? The geologic record, preserved in magnetized rocks, shows that our field has done something extraordinary hundreds of times in the past. It has completely flipped. A geomagnetic reversal is when the north and south magnetic poles trade places. This is a known part of the geodynamo's cycle. The last full reversal happened about 780,000 years ago. The process would not be instant. It would likely unfold over thousands of years. During that time, the field would not vanish, but it would grow much weaker and more complex, with multiple weaker, north, and south poles scattered across the globe. The consequences of living through such a time would be significant. With a weaker shield, more radiation from space would reach the surface. Our technology, especially satellites and power grids, would be far more vulnerable to solar storms. And the navigational abilities of many animal species would be disrupted. We have glimpses of what such a time might be like from smaller events in the past. The Loschamp event, about 42,000 years ago, was a temporary excursion where the field weakened dramatically. Studies suggest this period coincided with climate shifts and may have put stress on early human populations. The current weakening of the field and the rapid movement of the pole do not mean a reversal is about to happen. It could still be hundreds or thousands of years away. But they are a quiet reminder that the shield we depend on is not permanent. It is a living part of our planet's machinery, a restless giant whose behavior is still not fully understood. From the deepest part of the molten core to the highest reaches of the atmosphere, the Earth's magnetic field is a story of hidden connections. It connects the spin of our planet to the light in our skies. It connects the survival of a migrating animal to the function of our technology. It is an ancient, invisible framework that has allowed life to exist, protecting it from the vastness of space. We are living in a time when the dynamic nature of this field is becoming clearer. Its shifting poles and weakening strength are not a cause for alarm, but a call for humility. They are a reminder that the stability we assume is not guaranteed. We are passengers on a dynamic world, sheltered by a shield we are only just beginning to comprehend, a silent, powerful guardian that has quietly shaped our past and will, without doubt, determine our future. Earth's invisible shield is weakening and we should be worried. For billions of years, our planet has been held within an invisible field. It makes no sound. It exerts no force you can feel. And yet, it is the only thing that stands between the surface of our world and the constant flow of particles from the sun. It is a silent guardian, a planetary shield that preserves our atmosphere and makes life on Earth possible. But that shield is not static. It is changing, and we are only just beginning to understand what that means. Deep beneath our feet, in the molten heart of the world, a quiet drama is unfolding. Our planet's primary defense is slowly weakening. This isn't a story of sudden catastrophe. It is a story of slow, planetary change with consequences for the future of life on Earth. A story that is changing faster than we once thought. The invisible shield that makes life possible. So, what is this invisible shield? It helps to imagine Earth not just as a rock in space, but as a kind of enormous, complex magnet. The field it creates is a vast bubble that envelops our planet, called the magnetosphere. It extends from the very core of the Earth, thousands of miles down, stretching out far beyond the orbit of the Moon. Its origin is not a mystical force. It lies in a process happening deep within the planet's core, known as the geodynamo. Our planet is layered, like an onion. At its center is a solid inner core of iron and nickel, as hot as the surface of the Sun. Around this solid ball is the outer core, a moving ocean of liquid iron and nickel. This molten metal is in constant, slow motion. As heat escapes from the solid inner core, the liquid metal churns in massive, complex currents, like water boiling in a pot, but on a planetary scale. Because this moving liquid is a metal, it is electrically conductive. As this ocean of molten iron flows, it generates enormous electrical currents. These currents, combined with the steady rotation of the Earth, create our planet's magnetic field. It is a self-sustaining loop. The moving currents generate a field, and that field influences the flow of the metal, which in turn generates more of the field. It is a planetary engine that has been running quietly for billions of years. From this deep engine, the magnetic field lines arc outwards. They create a structure with two poles, a north and a south, much like a simple bar magnet. But this field is not a perfect, symmetrical bubble. Its shape is constantly being sculpted by a force from space, the solar wind. The Sun continuously sends out a stream of charged particles that travel at incredible speeds. This solar wind presses against our magnetosphere, compressing it on the side of the Earth facing the Sun. On the night side, the magnetic field is stretched out into a long tail, known as the magnetotail, that extends far past the Moon. Our shield is always being pushed, flexed, and reshaped. You move through this field every day, yet you cannot see it or feel it. Our bodies do not have the tools to sense magnetism. It passes through us as if we weren't there. And yet, there are moments when this invisible force makes itself known. When charged particles from the solar wind are guided down the magnetic field lines near the poles, they collide with atoms in our upper atmosphere. These collisions cause the atmospheric gases to glow. The result is one of the most beautiful natural displays on Earth, the aurora borealis and aurora australis. These shimmering curtains of light are, in essence, the magnetic field made visible, a rare glimpse of our silent protector at work. And while we may be unaware of it, many other living things are not. A wide array of organisms, from bacteria to turtles and birds, can sense the Earth's magnetic field. They use it to navigate during long migrations. They have an internal compass that we are only just beginning to understand. For them, the magnetic field is not invisible, it is a map, a guide that tells them which way is north. The life or death protector. The fact that we cannot feel the magnetic field does not change its importance. Without it, life as we know it could not exist. It is the single most important thing that makes our planet a habitable place in the cold of space. It is an active guardian, protecting us from the constant conditions of the cosmos. The first condition is the solar wind. Without the magnetosphere to deflect this steady stream of particles, it would directly strike our upper atmosphere. Over millions of years, this would act like a slow sandblaster, gradually stripping our atmosphere away. It would erode the ozone layer, which protects us from the Sun's harmful ultraviolet radiation. Without it, the surface of our planet would be bathed in levels of UV light that would make it uninhabitable for most life. The second condition comes from farther away. Our solar system moves through a galaxy filled with cosmic rays. These are high-energy particles accelerated to nearly the speed of light by distant cosmic events. Our magnetic shield deflects the majority of these particles, trapping them in two zones of radiation high above the Earth, known as the Van Allen belts. These belts hold the cosmic rays at a safe distance, preventing them from reaching the surface and damaging the DNA of living things. The third condition is the most energetic, coronal mass ejections, or CMEs. Sometimes, the Sun releases an enormous burst of plasma and radiation. When a CME strikes our magnetosphere, it triggers a geomagnetic storm, which causes the auroras we see. But most of the energy is guided around our planet, keeping us safe from the worst of the event. If you want a quiet, real-world example of what happens to a planet that loses its protection, You only need to look at our neighbor, Mars. Today, Mars is a cold, dry, radiation-soaked desert. Its atmosphere is less than 1% as thick as Earth's. But it was not always this way. Evidence suggests that billions of years ago, Mars was a warmer, wetter world, with a thicker atmosphere. It also had a global magnetic field. But for reasons scientists are still working to understand, the Martian geodynamo stopped. Its magnetic shield vanished. Without its shield, the solar wind fell upon Mars with its full, patient force. Over hundreds of millions of years, it stripped away the planet's atmosphere, carried away its water, and sterilized its surface. Mars became the world we see today. The story of Mars is a quiet cautionary tale, a planetary ghost that reminds us of the fragile nature of the shield that protects our own world. The magnetic field is the barrier that separates a living planet from a dead one. The hidden drama, its weakening. And this brings us to the heart of our story. The shield is not as constant as we once thought. For decades, scientists using satellites and observatories have been carefully measuring Earth's magnetic field. And they have come to a conclusion: it is weakening. This is not a distant problem. It is happening now. Data from the European Space Agency's swarm satellites has confirmed that the field has lost, on average, about 9% of its strength over the last 200 years. This weakening is not the same everywhere on the globe. In some areas, it is happening much faster. The most notable evidence of this is a large, growing region of magnetic weakness that stretches from South America across the southern Atlantic Ocean. Scientists call it the South Atlantic Anomaly, or SAA. The name is simple, but its meaning is significant. The SAW is a place where the shield is thinner than anywhere else. In this enormous region, the Van Allen radiation belts dip closer to the planet's surface. This has real-world consequences for our technology. Satellites passing through the SAW are exposed to higher levels of radiation, which can cause their electronics to malfunction. The problem is so consistent that operators of many satellites, including the Hubble Space Telescope, often power down sensitive instruments when their orbits take them through this region. It is a recurring quiet spot in our view of the universe, all because of this weakness in our planet's shield. And the anomaly is not still. It is growing and moving westward at about 20 kilometers per year. More than that, it appears to be splitting into two separate areas of weakness, which suggests that the processes in the Earth's core causing it are becoming more complex. The appearance of a second weak spot suggests the anomaly is part of a larger, more dynamic change happening deep within the Earth. Scientists are working to understand what causes the South Atlantic Anomaly. The leading idea is that it is the surface expression of a strange process happening at the boundary between the Earth's molten outer core and the solid mantle above it. They believe there may be a vast patch of liquid iron deep beneath southern Africa that is flowing in a reverse direction compared to the rest of the core. This patch could be creating a localized magnetic field that points in the opposite direction of the main field, effectively canceling a part of it out and creating the weakness we observe on the surface. The South Atlantic Anomaly serves as a quiet reminder that the magnetic field is not a simple, steady force. It is the product of a churning, molten interior. The weakening we see today is a surface-level symptom of a deep and hidden process, a slow shifting of forces within the heart of our world. The mystery of the core. To understand why the shield is weakening, we have to look past the symptoms and journey back to the source, the flowing engine of the Earth's core. The geodynamo is not a simple bar magnet. It is a complex system. The currents of liquid iron that generate the field are constantly shifting and swirling. As a result, the magnetic field they create is also in a constant state of flux. It strengthens, it weakens, and its poles wander. The magnetic poles are not fixed. The geographic north and south poles are stable points around which our planet rotates. The magnetic poles, however, are the points where the magnetic field lines are vertical. And these points move. For much of the 20th century, the magnetic North Pole drifted slowly, at about 10 to 15 kilometers per year. But in the 1990s, that began to change. The drift started to accelerate. In recent years, it has been moving across the Arctic at speeds of over 50 kilometers per year. It has moved so quickly that the scientists in charge of the World Magnetic Model, the model used in every smartphone and GPS system for navigation, have had to issue updates more frequently to keep up. Your phone's map knows where you are because it relies on this constantly updated model of our planet's shifting field. This rapid movement is another clear sign that something is changing within the core. Scientists believe the pole's accelerating drift and the weakening field in the South Atlantic are connected. They are both expressions of the same activity in the outer core. It seems there is a subtle tug-of-war between different parts of the field. For long periods, the main, simple field dominates. But there are always smaller, more complex fields churning away as well. Right now, it seems these more complex fields are gaining influence. This is not a new event. By studying the magnetic alignment of minerals in ancient lava flows, scientists have reconstructed the history of the Earth's magnetic field going back hundreds of millions of years. This record, written in stone, tells us that the field has always been a restless thing. It has gone through countless changes in strength and direction. There have been periods, called excursions, where the poles have wandered far from their usual positions before returning. The current weakening and rapid pole movement could be the beginning of one such excursion. Or, they could be symptoms of something more. The geological record is clear on one point. These periods of instability have, in the past, often been the prelude to a complete reversal of the Earth's magnetic field. Are the poles about to flip? This leads to the largest question. Is the current weakening a sign that the Earth's magnetic poles are about to flip? A geomagnetic reversal is what it sounds like. The north magnetic pole becomes the south, and the south becomes the north. A compass that once pointed north would, after a reversal, point south. It sounds dramatic, but the rock record shows us it is a natural part of our planet's life cycle. Reversals have happened hundreds of times. They do not seem to happen at regular intervals. The last full reversal occurred about 780,000 years ago. By some measures, we are overdue for another. So, is a flip about to happen? The answer, according to most scientists, is probably not. At least, not soon, and not in the way one might imagine. A geomagnetic reversal is not an instantaneous event. The poles do not just switch places overnight. It is a long process that can take thousands of years to complete. During this period, the magnetic field would not disappear. It would become much weaker and far more complex. The simple field with one north and one south pole would break down. It might be replaced by a messy field with several weaker, north, and south, poles scattered across the globe. For a time, a compass might point somewhere entirely unexpected. This long period of magnetic change is the real area of study. During a reversal, the shield's strength could drop to as low as 10% of what it is today. Weak spots like the South Atlantic Anomaly might become more common, or the entire globe could become a kind of large, weak anomaly. The protection we are used to would be much lower, leaving our planet more open to the environment of space. There is no evidence in the fossil record to suggest that past reversals have caused mass extinctions. Life has survived hundreds of these events. But there is a key difference between now and 780,000 years ago: our global, technological civilization. We are the first species with advanced technology to experience such a planetary shift, and in many ways, we are uniquely exposed. While a full reversal is likely thousands of years away, the current weakening is happening now. The changes are real and measurable. We may not be on the edge of a full flip, but we are in a time of significant geomagnetic change. We are heading into a period where our shield will be weaker than it has been in recorded human history. What a weaker shield means for us. The effects of a weaker magnetic shield are not abstract. They touch on nearly every part of modern life. First is the risk to our technological infrastructure. Our civilization is built on electricity and electronics, and this system is vulnerable to space weather. During a period of a much weaker magnetic field, a powerful CME would have a greater effect. The influx of particles could induce strong electrical currents in long conductors on the surface, like power grids. These currents could overload transformers, causing them to fail on a large scale. In 1989, a moderate solar storm did just that, collapsing the power grid of Quebec. With a much weaker shield, a similar storm could have a much wider impact. Our satellites, which we rely on for communications, weather forecasting, and GPS, would be at greater risk. Without the full protection of the magnetosphere, they would be exposed to more radiation, more often. Satellite failures could become more common. GPS systems could become less reliable, affecting everything from aviation to the map on your phone. Beyond technology, there would be consequences for life itself. A weaker shield means more radiation from space would reach the Earth's surface. This would not be an instantaneous danger, but the increase in background radiation levels could lead to an increased risk of certain health problems over time. Then there is the impact on the natural world. We know that many species rely on the magnetic field for navigation. During a period of a complex, multipolar field, their internal compasses could become difficult to use. This could cause disorientation and affect migrations for populations that travel long distances to breed and find food. We do not know how these species would cope with the loss of a sense they have relied on for millions of years. And on the longest of timescales, there is the atmosphere. A weaker shield makes our planet more vulnerable to atmospheric stripping by the solar wind. This is a very slow process, but it is the same one that changed Mars from a potentially habitable world into a desert. It quietly underscores the importance of the geodynamo, not just for our daily lives, but for the long-term future of our planet. The race to understand. Faced with this situation, scientists are not standing still. We are in a time of remarkable discovery in geomagnetic research. For the first time, we are able to monitor these planetary changes in real time. The primary tool in this effort is the European Space Agency's SWARM mission. Launched in 2013, this trio of satellites flies in a unique formation, taking precise measurements of the strength and direction of the Earth's magnetic field. SWARM's data is what has allowed scientists to map the South Atlantic Anomaly so precisely and to track its movement. It is also providing information about the behavior of the iron churning in the Earth's core. By combining satellite data with measurements from the ground and complex computer models, researchers are slowly piecing together a more complete picture of what is happening thousands of miles beneath our feet. They are trying to answer the most important questions. How fast will the field continue to weaken? Will the South Atlantic Anomaly continue to grow? And what is the likelihood of a major excursion or reversal in the coming centuries? This research has practical applications. By better understanding how the field changes, scientists can improve their models of space weather. This allows for better warning systems for solar storms, giving grid operators and satellite controllers time to take protective measures. Understanding the movement of the magnetic poles is essential for maintaining the accuracy of all navigation systems. We are, in a very real way, the first generation of humans to be aware of our planet's magnetic vulnerability. We are the first to have the tools to watch this quiet drama unfold. The work of these scientists is a race to understand the fundamental workings of our planet, so that we can prepare for the changes that are to come. We live on a dynamic planet. The ground feels solid, but deep within, our world is in constant, quiet motion. The same inner turmoil that powers volcanoes and shifts continents also generates the invisible shield that protects us. For billions of years, that shield has held, deflecting the conditions of space and allowing life to flourish. But now, we have learned that this shield is not unchanging. It is weakening, shifting, and becoming more complex. We are living in an era of geomagnetic change, a time when our planet's defense is less reliable than it has been for a very long time. The South Atlantic Anomaly is a quiet, visible warning of this new reality. We are not on the verge of an apocalypse, but on the verge of a new understanding of our relationship with our planet. The mystery of the weakening shield is a story of scientific inquiry, of technological vulnerability, and of the deep, hidden forces that govern the fate of our world. It's a reminder that we are passengers on a small, fragile oasis, protected by a silent guardian that is more dynamic, and perhaps more temperamental, than we ever knew. The greatest drama on Earth may not be happening on its surface, but in its deep, molten heart. What if Earth's shield vanished for 24 hours? Every second, you are protected. Not by a person or a technology, but by an invisible field of energy. It is a silent guardian, a planetary shield generated by the churning, molten heart of our world. This is Earth's magnetic field, a bubble that extends tens of thousands of kilometers into space, deflecting a constant storm of particles hurled at us by our own sun. We live our entire lives inside this protective space, never feeling it, never seeing it, but owing our existence to it. It is one of the reasons our planet is a vibrant, water-filled haven for life and not a barren, sterilized rock like Mars. But what if, for just 24 hours, it stopped? This is a journey through what that day might look like. We will explore what would happen to our technology, to our bodies, and to life itself. What would be the first thing to go? How long would the modern world last? And could life itself survive a day without its shield? The first hour, the silent onset. The first few minutes would be quiet. On the surface of the Earth, the sun would rise as it always does. The morning would begin. You would not feel a thing. The event begins not with a sound, but with a silent, invisible change in physics. The moment the magnetic field disappears, Earth becomes an exposed target. The first wave of this exposure comes from the solar wind. This is a superheated plasma, a torrent of charged particles, mostly protons and electrons, blasting away from the sun at over 1,000,000 miles per hour. For billions of years, our magnetosphere has stood against this cosmic stream, deflecting its particles harmlessly around our planet. With the shield gone, this stream of radiation now strikes the upper atmosphere directly. At the same time, another force arrives: galactic cosmic rays. These are high-energy particles, accelerated to nearly the speed of light by distant cosmic events. Our magnetic field, along with our atmosphere, has always served as our planetary armor against these microscopic particles. Now, part of that armor is gone. The first victims of this new environment are not on Earth, but above it. Circling our planet are thousands of active satellites. They are the backbone of global communication, navigation, financial transactions, and weather forecasting. And they are now completely exposed. Within the first hour, the effects begin. Satellites are not designed to withstand a direct, unfiltered blast of solar particles. Their delicate electronics are bombarded. These particles can cause what engineers call single-event upsets, flipping bits in a satellite's memory from ones to zeros and zeros to ones, corrupting software and causing systems to crash. Components begin to short-circuit. The Van Allen belts, two zones of radiation that were held in place by the magnetic field, are now gone, their energy washing over everything in orbit. On the ground, the first signs of trouble are subtle. Your GPS might take a few extra seconds to find your location. An international news channel might flicker. A long-distance phone call could drop. These are the first indications of a world becoming disconnected. High above, the intricate web of technology that connects billions of people is beginning to fail, one satellite at a time. The first hour has only just begun, but the groundwork for a global shutdown is being laid, even if it is not yet understood. Hours 2 to 6. The technological cascade. As the clock moves into the second hour, the subtle glitches escalate into a systemic failure. The loss of satellites is now a cascade. GPS, the system that guides everything from cars to global shipping, is the first to go completely dark. Every plane in the sky and every ship at sea suddenly loses its primary means of navigation. Air traffic controllers look at blank screens, their ability to manage aircraft vanishing. The world's communication networks follow. The satellites that relay television, internet, and phone calls are overwhelmed. International communication ceases. The internet, reliant on a global network of undersea cables and satellite links, begins to fracture. Financial markets, which depend on precise timing signals from GPS satellites, are thrown into chaos before they, too, go offline. The modern world, built on a foundation of interconnected data, is being unplugged from itself. But a more fundamental failure is happening on the ground. As the solar wind continues to strike the planet, a new phenomenon takes hold: geomagnetically induced currents, or GICs. The planet's atmosphere and the ground itself become electrically charged by the constant bombardment of particles. This creates vast, unpredictable flows of direct current, DC, that surge through the Earth. Our power grids, with their thousands of miles of transmission lines, act as giant antennas for this energy. These long power lines absorb the GICs, funneling massive DC currents into the high-voltage transformers that form the heart of the grid. Transformers are designed for alternating current, AC, not this surge of DC. The effect is catastrophic. The DC current pushes the transformers into what is called half-cycle saturation. Their magnetic cores are overwhelmed, and they begin to overheat at an astonishing rate. All across the globe, the hum of substations changes. Safety relays begin to trip, trying to isolate the damage, but the problem is too widespread. In cities and towns across continents, massive transformers begin to fail, some violently. They can spew their insulating oil, which can ignite and send plumes of smoke into the sky. The grid collapses in a chain reaction. As one section fails, it overloads the next. First, a city goes dark. Then a region. Then an entire country. Within a few hours, the lights go out all over the world. North America, Europe, Asia, all plunged into an unprecedented blackout. For the average person, this is the moment the new reality sets in. One moment, you're reading panicked reports on your phone. The next, your screen is dark. The lights go out. You look out the window and see a darkness stretching to the horizon, unbroken by the familiar glow of a city. There is no signal. The radio is silent. The internet is gone. Humanity has been returned to a pre-electric age, not over generations, but in the span of a single morning. We are now isolated, disconnected, and living in a new, quiet dark. The technological world is gone. Hours 7 to 12. The biological impact. As midday approaches, the focus shifts from our machines to our biology. The threat is no longer just to our infrastructure, but to our bodies. With the magnetic shield gone, the solar wind's assault begins to tear apart another critical layer of protection: the ozone layer. The ozone layer is a shield within our stratosphere that absorbs the most harmful frequencies of ultraviolet radiation, specifically UVB and UVC. The protons in the solar wind are effective at destroying ozone molecules. Without the magnetic field to guide these particles toward the poles, they are now striking the entire upper atmosphere, rapidly depleting our planetary sunscreen. The effects on the surface become noticeable quickly. The sunlight feels different. Anyone outdoors for even a few minutes would experience a sunburn more severe and rapid than anything they have ever felt. The UV index, a scale normally capped around 11 or 12, would soar into the hundreds. Unprotected exposure would become a medical emergency. People retreat indoors, into the darkness of the global blackout. The world outside is now dangerously bright. In the long term, skin cancer rates would rise dramatically, but the immediate threat is radiation burns and severe eye damage. For astronauts on the International Space Station, now without the protection of the magnetosphere, the radiation dose is lethal. They may experience strange flashes of light inside their eyes, a known phenomenon caused by cosmic rays passing through their retinas. The animal kingdom is thrown into chaos. Many species depend on an internal magnetic sense for survival. This ability, called magnetoreception, is their internal GPS. And it has just been erased. Migratory birds suddenly have no idea which way is south for the winter. They fly in confused circles until they fall from exhaustion. Sea turtles, on their long journeys to nesting beaches, are now lost at sea. Whales, sharks, and even honeybees are disoriented, their internal compasses spinning uselessly. The intricate choreography of migration, a dance millions of years in the making, has come to a halt. Even the foundation of the food web, the plant kingdom, is under attack. The intense UV radiation is damaging leaves and plant cells, disrupting the process of photosynthesis. Plants begin to struggle to convert sunlight into energy. The very bottom of the food chain is being damaged by the sun. By noon on the first day, the planet is transformed. Technology is a relic. The sun has become a source of harm. And the symphony of the natural world has become a cacophony of confusion. The invisible shield was more than a protection for our technology. It was a fundamental component of the biosphere. And now, life itself is beginning to unravel. Hours 13 to 23, the world transformed. As the day turns into an unfamiliar night, the planet itself begins to look alien. The most spectacular transformation is painted across the entire sky. Auroras, the lights once confined to the polar regions, are now a global phenomenon. This is not the gentle aurora borealis of Arctic postcards. This is a planet-wide light show, a visible testament to the atmosphere's interaction with the solar wind. With no magnetic field to funnel particles to the poles, they now strike the atmosphere at every latitude. The sky ignites from horizon to horizon in a display of colors, greens, reds, purples, and blues, all swirling in a perpetual, silent storm. This glow is so intense it turns night into a strange twilight. These are not lights of wonder, they are the signs of atmospheric erosion. The solar wind is no longer just interacting with our atmosphere, it is stripping it away, just as it did to Mars billions of years ago. High-energy particles collide with atoms of oxygen and nitrogen, giving them enough energy to escape Earth's gravity and bleed out into space. It is a slow process, but we are witnessing its beginning. Ton by ton, our atmosphere is being lost to space with every passing hour. On the ground, society is breaking down. The loss of technology was a shock, but the new physical reality is different. There is no power, no communication, no running water in most cities. The world is dark and silent, yet the sky above pulses with an unnatural light. Governments are as powerless as their citizens, with no way to communicate or coordinate. The human experience is reduced to its essentials. The search for safe water, for food, for shelter from a sun that has become harmful. People huddle in their homes, in basements, in any structure that offers protection from the UV rays. There is a profound terror in knowing that the fundamental rules of the world have changed. The sky is no longer safe. The sun is no longer just life-giving. The blue planet is transforming. It is becoming a wounded world, scarred by the loss of its invisible guardian. The auroras paint the sky with the beauty of destruction. The atmosphere thins, particle by particle. Life on Earth is now living on borrowed time, trapped between the darkness of a dead civilization and a sky filled with deadly light. Hour 24, the brink. We have reached the end of the 24th hour. The planet that emerges is a shadow of its former self. Let us take stock. Our technological civilization is gone. The global power grid is a ruin, with thousands of essential transformers destroyed. Even if the shield were to return now, it would take years, perhaps decades, to manufacture and replace them. Most of the world's population is without electricity for the foreseeable future. Communication is local, reduced to the range of a human voice. The biosphere is in crisis. The damage from ultraviolet and cosmic radiation is severe. Plant life is scorched. Animal populations are in disarray, their navigational abilities gone. For humanity, the short-term radiation exposure has led to widespread burns and eye damage. The long-term consequences, cancers and genetic mutations, are a ticking time bomb coded into the DNA of every survivor. The planet itself is physically altered. The atmosphere is thinner than it was 24 hours ago. The process of atmospheric stripping, the same that rendered Mars desolate, has begun. The auroras continue to writhe across the globe, a constant visual confirmation that our world is being actively eroded. The Earth is not dead. Not yet, but in just 24 hours, it has been set on a path toward becoming the next Mars. The invisible architecture that made life possible has been broken. The systems are unraveling. Life, in its most tenacious forms, would likely survive. Bacteria deep underground or near hydrothermal vents might be shielded. But surface life, the complex tapestry of plants and animals we know, is facing an extinction-level event. Humanity, stripped of its technology, faces a fight for survival in a world that has become hostile. This is the state of the Earth after one day without its shield. A world plunged into darkness, harmed by its own star, and slowly having its breath stolen away into the void. The 24 hours are up, and as the clock strikes the final second, a switch is flipped deep within the planet's core. And just like that, it is back. The geodynamo spins back to life, and the magnetic field snaps back into place. Instantly, the solar wind is deflected. The cosmic rays are herded away. The planet-wide auroras vanish, receding to the poles where they belong. The bombardment ceases. The planet is safe again. But the scars of this one day will last for generations. The technological world remains in ruins. Rebuilding the grid would be a monumental task, undertaken by a species struggling with societal collapse. The biosphere is deeply wounded. Many species may never recover. The spike in radiation has sown the seeds of disease that will be reaped for decades. The world would survive. Humanity would survive. But we would be forever changed by the memory of the day the sky turned against us. There is, however, good news. This scenario, a sudden, complete disappearance of our magnetic field, is not something that can happen. Our planet's molten core, the engine that powers the geodynamo, has been churning for over 4 billion years and will continue to do so for billions more. The field does change. It weakens, it strengthens, and it even flips its poles every few 100,000 years or so. We know from the geologic record that these reversals are lengthy processes, taking thousands of years. During that time, the field never disappears entirely. It becomes weaker and more complex, with multiple north and south poles, but a baseline level of protection always remains. So, you do not need to worry about waking up to a technological apocalypse. But this thought experiment tells an important story. We live on a fragile oasis in a violent universe. We are protected by forces we can neither see nor feel, forces that have silently guarded every living thing that has ever existed. That invisible field is as essential to us as the air we breathe and the water we drink. It is the silent hero of our planet's story, the guardian that makes our living world possible. What if scenario should we explore next? A world without the moon? Or what if a black hole entered our solar system? Let us know in the comments below, and feel free to subscribe for more journeys into the impossible. The unseen force secretly protecting you from annihilation. You cannot see it, you cannot feel it, but in this moment, an unseen force is the only thing standing between you and the quiet emptiness of space. It is a power born in the heart of our world, an ancient and colossal presence that has silently guarded the planet since the first beginnings of life. If this guardian were to vanish, the consequences would be almost immediate and completely catastrophic. The air you breathe would be slowly stripped away, scoured from the globe by a relentless wind flowing from the sun. Our oceans, the cradle of life, would boil and fade into the vacuum. The surface of our world, now so full of life, would be bathed in a constant barrage of cosmic rays, particles that would shred the very building blocks of biology. Earth would fall silent, becoming a barren rock, much like our planetary neighbor, Mars. So, what is this invisible protector? What is this quiet shield that allows our world to remain alive? This is the story of Earth's magnetic field, the silent defender that has protected you every second of every day for your entire life. It is a story that begins not on the surface, but thousands of miles beneath your feet, in a churning, fiery furnace that dictates the fate of everything. To understand this force is to understand not just a curious piece of planetary science, but one of the fundamental reasons we are here at all. It's a tale of cosmic pressure, planetary resilience, and the beautiful, intricate dance of physics that makes a living Earth possible. Imagine, for a moment, a world without it. It is not a difficult picture to paint. We have a perfect example orbiting the Sun not too far from us. Mars, a planet that we now know once had oceans, a thicker atmosphere, and perhaps, even the first stirrings of life. But billions of years ago, Mars lost its global magnetic field. Its core cooled, the engine that powered it sputtered and died, and its shield vanished. Without that protection, the solar wind, a constant stream of charged particles from the Sun, crashed into the Martian atmosphere. Over millions of years, it stripped that atmosphere away, molecule by molecule. Its water disappeared, its air thinned to less than 1% of Earth's, and its surface was left exposed to the full, sterilizing glare of cosmic radiation. Mars became the frozen, red desert we see today. This is the fate that may await any world that loses its planetary shield. This is what could happen to Earth if our own magnetic field were to fail. The daily pressure our planet endures is almost unimaginable. Every moment, the Sun ejects a torrent of plasma, the solar wind, traveling at speeds that can exceed 1,000,000 miles per hour. This isn't a gentle breeze. It is a high-energy flow of protons and electrons that, if it were to reach us unchecked, would erode our atmosphere in the same way a sandblaster strips paint from a surface. Life on Earth was able to develop, and continues to be sustained, only because of the protection this magnetic environment provides. Without it, there would be no us, no future. Just a slow, inevitable decay into a barren world. The stakes are, quite literally, life and death on a planetary scale. The dragons are shield slays. To truly appreciate the Guardian, you must first understand the dragons it slays. The universe, for all its beauty, is an intensely hostile place. Our planet is constantly swimming through a sea of invisible but incredibly powerful threats. The primary and most persistent of these is the solar wind. Born from the Sun's scorching corona, its 2 million-degree upper atmosphere, the solar wind is a continuous outflow of charged particles, mostly protons and electrons, blasted into space in every direction. These particles travel at incredible velocities, ranging from 250 to 500 miles per second. This is not an empty stream, it is dense with energy. The Sun loses over 1 million tons of material every single second to this wind. When this river of plasma reaches Earth, it carries with it the Sun's own magnetic field. The interaction between our field and the Sun's is what defines the entire battleground of our planet's defense. But the solar wind is just the baseline. The Sun is a dynamic, often violent star. It has weather, and its storms are far more terrifying than any on Earth. The two most significant forms of this solar weather are solar flares and coronal mass ejections, or CMEs. Solar flares are intense bursts of radiation from the Sun's surface. They are born from the sudden, explosive realignment of magnetic field lines, releasing a tremendous amount of energy in the form of radiation, from radio waves to X-rays and gamma rays. Because this radiation travels at the speed of light, we have no warning. A flare that erupts on the Sun is felt here just 8 minutes later. Thankfully, our atmosphere and magnetic shield protect us on the ground from direct harm. But for anything outside that protection, like satellites or astronauts, it's a different story. Then there are the coronal mass ejections. CMEs are the real planetary heavyweights. These are colossal explosions that hurl billions of tons of plasma and magnetic fields into space. Imagine a cloud of superheated gas, wider than dozens of Earths, weighing more than Mount Everest, traveling at several million miles per hour. If a flare is like the muzzle flash of a cannon, a CME is the cannonball. When a CME is aimed at Earth, its impact is monumental. It slams into our magnetic shield, compressing it violently and transferring an enormous amount of energy into our system. This is what triggers the most severe geomagnetic storms. The most famous example is the Carrington event of 1859. A massive CME struck Earth, and the storm was so powerful it induced electrical currents in telegraph wires, shocking operators and, in some cases, setting paper on fire. Auroras, the beautiful light shows normally seen near the poles, were visible as far south as Cuba and Hawaii. If a storm of that magnitude happened today, the consequences for our technology would be catastrophic. It could cause widespread power blackouts, cripple satellite networks, and take down GPS and communication systems around the world. Beyond the Sun, there are galactic cosmic rays, or GCRs. These are high-energy particles, the shattered remnants of atoms accelerated to nearly the speed of light by distant, exploded stars. They are the atomic shrapnel of supernovae, constantly raining down on our solar system. Our magnetic shield, along with the Sun's, deflects the vast majority of these, but they are so energetic that some still get through. They pose a significant radiation hazard to astronauts on long missions, and a world without a magnetic field would be utterly exposed to their self-shredding effects. This is the chaotic, energetic environment our planet navigates every single day. We are adrift in a cosmic shooting gallery. The only reason we are not just aware of this, but alive to even contemplate it, is because of the incredible, invisible fortress generated from the very heart of our world. Forging the shield, a journey to the center of the Earth. So where does this planetary force field come from? The answer lies not in space, but deep within the Earth, some 1,800 miles beneath our feet. The source of our magnetic shield is the planet's core. To understand its creation, we must first journey to this incredibly remote region. Our planet is structured in layers, like an onion. We live on the crust, a paper-thin layer of solid rock. Beneath that is the mantle, a vast region of semi-molten rock that churns in slow motion over millions of years. At the center is the core, and it is divided into two parts: a solid inner core and a liquid outer core. The inner core is a sphere of solid iron and nickel, roughly the size of the Moon. The pressure here is immense, over 3.6 million times that of the surface, which is why it remains solid despite temperatures hotter than the surface of the Sun. Surrounding this solid ball is the outer core, a 1,400-mile thick ocean of liquid iron and nickel. This swirling, molten metal is the engine of our magnetic shield. It is here that the geodynamo is born. The process is driven by heat. The solid inner core, while slowly cooling, radiates heat outwards into the liquid outer core. This creates convection currents, much like the churning you see in a pot of boiling water. Hotter, less dense molten iron rises, cools as it approaches the cooler mantle, and then sinks back down. This creates immense, slow-moving plumes of flowing liquid metal. But this isn't just a simple boiling motion. The Earth's rotation adds a crucial second ingredient: the Coriolis force. The same force that creates the spiral patterns of hurricanes on the surface acts on these columns of molten iron, twisting them into complex, spiraling shapes. Here's where the process becomes self-sustaining. Molten iron is an electrical conductor. When you move a conductor through a magnetic field, you generate an electric current. It's the principle of a dynamo. But where did the first magnetic field come from? The answer is that it only needed a tiny seed to start, perhaps from the sun itself. As the swirling columns of iron moved through this weak seed field, they generated electric currents. These electric currents, in turn, generated their own magnetic fields. As the spirals of molten metal twisted and churned, they amplified these new fields. The movement creates currents, the currents create a magnetic field, and that stronger field allows the movement to create even stronger currents. It is a feedback loop of immense power, converting the thermal and kinetic energy of the planet's core into electromagnetic energy. This is the geodynamo effect. The result is a large, stable magnetic field that approximates a dipole, with a north and a south pole, much like a bar magnet. This field is powerful enough to extend far out into space, enveloping our planet. It is not perfectly aligned with our planet's axis of rotation. It's tilted, which is why geographic north and magnetic north are in two different places. This magnetic North Pole is famously on the move, currently drifting from the Canadian Arctic towards Siberia. Its speed has fluctuated, peaking at over 55 kilometers per year in the 2000s and more recently slowing to around 35 to 45 kilometers per year. This movement is a quiet reminder of the dynamic, ever-changing nature of the liquid core far below. This entire process is a delicate balance. It requires a planet to be large enough to hold its internal heat, to have a liquid core, and to spin fast enough to create the necessary twisting forces. This is why Earth has a strong magnetic field, while Mars and Venus do not. Mars is too small, its core cooled. Venus spins far too slowly. Earth is in a Goldilocks zone, not just for liquid water, but for a life-sustaining geodynamo. It is a planetary engine, forged in fire and pressure, that has been running for billions of years, tirelessly generating the shield that makes our world a haven. The shape of our defense. This colossal magnetic field, generated in the core, extends tens of thousands of miles into space, creating a vast, invisible structure known as the magnetosphere. This is the region where our planet's magnetic field is the dominant force. It is our first and most important line of defense. The shape of the magnetosphere is not a perfect sphere. Instead, it is molded by the constant pressure of the solar wind, creating a dynamic, comet-shaped bubble. On the side facing the sun, the day side, the solar wind slams into our magnetic field, compressing it to an altitude of only about 40,000 miles. On the side of the Earth facing away from the sun, the night side, the story is very different. Here, the solar wind stretches the magnetosphere out like a windsock, creating a long magnetotail that extends for hundreds of thousands of miles, far beyond the orbit of the Moon. But the shield is not impenetrable. Through a process called magnetic reconnection, the Sun's magnetic field can link up with Earth's, creating temporary openings. This allows a flood of energy and particles to pour into our magnetosphere, powering geomagnetic storms and the brilliant auroras. NASA's Magnetospheric Multiscale (MMS) mission, a fleet of 4 spacecraft, was specifically designed to study this complex process, giving us an unprecedented look at how our shield bends and sometimes breaks under the solar assault. Inside the magnetosphere are other critical structures, most famously the Van Allen radiation belts. Discovered in 1958, these are 2 donut-shaped zones of highly energetic charged particles trapped by the magnetic field. The belts act as a kind of radiation trap, capturing dangerous particles and preventing them from reaching the surface or low Earth orbit, where the International Space Station resides. The magnetic field lines that create this system curve out from the South Pole and loop back in at the North Pole. At the poles themselves, the field lines are nearly vertical, plunging directly into the atmosphere. This creates two weak points, known as the polar cusps, where particles from the solar wind can funnel directly down. When these solar particles collide with atoms of oxygen and nitrogen in our upper atmosphere, they excite those atoms. As the atoms return to their normal state, they release this excess energy as light. This is the aurora borealis in the north and the aurora australis in the south. The different colors are produced by different atoms at different altitudes. Green comes from oxygen, while vibrant purples and blues come from nitrogen. The aurora is, in essence, the visible evidence of our magnetic shield in action. It is the beautiful, ethereal glow of a planetary defense system at work. A shield in motion. Our magnetic shield, for all its power, is not a permanent fixture. It is a dynamic, fluid entity that weakens, strengthens, and shifts over time. And recent observations have shown that it is currently undergoing some very significant and rapid changes. Over the last 2 centuries, the global strength of the magnetic field has declined by about 9%. Some more recent data has suggested the rate of weakening could be as high as 5% per decade, which is 10 times faster than previously thought. This weakening is not uniform. The most prominent area of weakness is a vast region stretching from South America across the southern Atlantic, known as the South Atlantic Anomaly, SAW. Here, the magnetic field is significantly weaker, allowing the Van Allen radiation belts to dip much closer to the Earth's surface. While this poses no direct threat to life on the ground, it is a known hazard for satellites, which can experience technical malfunctions when passing through the region. Data from the European Space Agency's swarm satellites show that this anomaly is not only deepening but also expanding. More curiously, recent observations suggest it may be splitting into 2 separate lobes, or cells, a development scientists are closely monitoring for what it might tell us about the processes happening in the Earth's core. This weakening naturally leads to a dramatic question. Is the field about to flip? A geomagnetic reversal, where the north and south magnetic poles swap places, is a normal part of our planet's behavior. The geological record shows these reversals have happened hundreds of times. They don't happen on a regular schedule, but the last full reversal was the Brunhes-Matayama reversal, around 780,000 years ago, which means we are, statistically, somewhat overdue. What would a reversal look like? It would not be an instantaneous flip. The process would likely take thousands of years. A 2019 study estimated the last reversal took 22,000 years to complete. During this transition, the main field would weaken, and multiple, smaller magnetic poles might appear across the globe. The consequences for life would likely not be apocalyptic. There is no evidence in the fossil record of mass extinctions being linked to reversals. Even at its weakest, the field and our thick atmosphere would still provide substantial protection. However, the consequences for our technological civilization could be severe. A weaker field would make our power grids and satellite infrastructure far more vulnerable to solar storms. Navigation that relies on the magnetic field would become complicated. While scientists see no signs of an imminent reversal, the current changes are a quiet reminder that the shield we depend on is not a constant. The silent partner to life. While the magnetic field's most dramatic role is as a planetary shield, its influence may be deeper and more subtle than just protection. For billions of years, it has been a silent partner in the story of life, an invisible environmental factor that some living things have learned to sense and use. This ability is called magnetoreception. The most famous examples are migratory birds. For decades, scientists puzzled over how birds could navigate with such accuracy over thousands of miles. We now know they use an internal magnetic compass. They can literally sense the Earth's magnetic field lines. The leading theory suggests a protein in their eyes, called cryptochrome, is sensitive to the magnetic field, allowing the birds to receive a visual pattern of the field overlaid on their normal vision. But it's not just birds. Sea turtles, salmon, and even simple bacteria use the magnetic field to orient themselves and navigate their worlds. For these creatures, the field is a tangible part of their environment, as real as the ground beneath them. The field's influence may extend even deeper into our planet's history. Recent research has uncovered a startling discovery. Over the past 540 million years, the strength of Earth's magnetic field and the concentration of oxygen in the atmosphere appear to have risen and fallen in a closely correlated pattern. When the field was strong, oxygen levels tended to be high. When the field was weak, oxygen levels tended to fall. This doesn't necessarily mean a stronger field directly locks in more oxygen. Instead, researchers speculate that both could be influenced by a common process deep within the planet. The same powerful forces in the core that drive the geodynamo might also influence processes in the mantle above, which in turn could affect volcanic activity and the release of gases that regulate the long-term oxygen cycle. This incredible link suggests that the habitability of our planet, the very evolution of complex, air-breathing life, is intimately tied to the fiery engine in the planet's core. The shield and the atmosphere it protects may be two parts of a single, deeply interconnected life support system. Deep beneath your feet, an ocean of liquid iron churns in a dance that has lasted for billions of years. It is a process of unimaginable scale and power, driven by the ancient heat of our planet's formation. From this fiery chaos emerges a silent, invisible elegance, a magnetic field that envelops our world, a guardian that stands vigil against the steady pressure of the cosmos. This field is the unseen force that has allowed life to take root and flourish. It deflects the solar wind that would otherwise strip away our air and our oceans. It stands guard against cosmic rays that would harm life on the surface. It is the reason we live on a vibrant blue world instead of a silent red one. It is a shield, a navigator, and a quiet partner to life itself. We see its work in the ghostly, beautiful dance of the auroras, a visual reminder of the constant, quiet protection being waged on our behalf. And yet, this shield is not invincible. It is a dynamic thing, weakening in places, with poles that wander. These changes are a powerful reminder of the delicate balance that makes our existence possible. They compel us to study and understand this force, not just out of scientific curiosity, but out of an appreciation for our own place in the universe, and the profound gift of living on a protected world. So the next time you look up at the sky, remember the unseen. Remember the churning heart of the Earth, thousands of miles below, generating a silent, invisible power. Remember the cosmic shield that is, in this very moment, protecting you, the air you breathe, and everything you have ever known. If this kind of calm exploration into the world around us helps you unwind, consider liking the video and subscribing to the channel. And for another look at the cosmic forces that shape our world, you might enjoy our next video on the awesome and terrifying power of black holes. The journey is just beginning. A 5,000 degrees Celsius ocean in Earth's core is saving your life. There is a constant, invisible storm moving through the solar system. It is a relentless wind of charged particles, flowing from the sun at over 1,000,000 miles per hour. By all accounts, this solar wind should be devastating to a world like ours. Over deep time, it has the power to strip away an atmosphere, molecule by molecule, until the oceans boil into space and the surface is left barren and sterilized. We can see evidence of this process on our planetary neighbor, Mars. So, a quiet question presents itself. Why is Earth different? Why are our oceans full and our skies blue? The answer is found deep beneath our feet. Thousands of kilometers down, there is a hidden world of immense heat and motion. A swirling, turbulent ocean of liquid metal, hotter than the surface of the Sun, is churning without pause. This planetary engine generates an invisible field, a silent guardian that envelops our entire world. This is a journey to the center of the Earth. Not to find monsters or myths, but to understand this impossible ocean, to uncover how it works, and to see why it is one of the most important things protecting life as we know it. The invisible shield. Before we look down into the Earth, we must first look out into space to appreciate the forces at play. The Sun is not a gentle, static ball of light. It is a chaotic nuclear furnace, constantly ejecting a supersonic stream of plasma, protons and electrons, in every direction. This is the solar wind. It is not a breeze, but a particle storm of immense and sustained energy. For an unprotected planet, this storm is quietly catastrophic. Over millions of years, it acts as a sandblaster on a planetary scale, eroding an atmosphere. We have a clear and tragic example of this nearby. Mars was once a world with a thicker atmosphere, and perhaps liquid water. Today, it is a cold desert, with an atmosphere less than 1% as dense as Earth's. The primary reason for this change was the solar wind. The planetary engine of Mars died billions of years ago, and without its protection, the solar wind slowly stripped its atmosphere away, turning a potentially habitable world into a desolate one. Earth, however, avoided this fate. Our planet has a different kind of protection, the magnetosphere. Generated from deep within the planet, Earth's magnetic field extends tens of thousands of kilometers into space, forming a vast, invisible bubble around us. As the solar wind approaches, it first impacts the outer boundary of this bubble, creating a supersonic shockwave known as the bow shock. The effect is not unlike the wave that forms at the bow of a ship as it moves through water. At this boundary, the magnetosphere deflects the vast majority of the solar wind's charged particles, forcing them to flow around our planet. This constant pressure squishes the magnetosphere on the side facing the Sun and stretches it into a long tail on the night side, like a windsock extending for hundreds of thousands of kilometers. This shield is our planet's first line of defense. Without it, the slow erosion that sterilized Mars would have happened here. Our atmosphere would have thinned. Our oceans would have vanished. Life as we know it would be impossible. The shield is not perfect. Some high-energy particles penetrate its outer layers, becoming trapped in two donut-shaped zones of radiation that encircle our planet, known as the Van Allen belts. Other particles are funneled along the magnetic field lines toward the poles. When these captured particles collide with oxygen and nitrogen atoms in our upper atmosphere, they release their energy as light. This is the only time we can see our planetary shield in action. The quiet, shimmering curtains of the aurora borealis and aurora australis. They are a beautiful reminder of the constant, invisible process happening far above our heads. So, where does this life-saving force field come from? It is not generated by a giant, solid magnet. The truth is more complex and more dynamic. To find its source, we must begin a journey downward, through the layers of our own world. The journey to the center of the Earth. To understand the origin of our magnetic shield, we can peel back the layers of the planet. The part we are familiar with, the ground beneath our feet, is the crust. In the grand scheme of the planet, the crust is remarkably thin, in most places, only 30 to 50 kilometers deep. Relative to the size of the Earth, it is thinner than the skin of an apple. Beneath the crust lies the mantle. This is the largest layer of the Earth, a colossal region of silicate rock that extends down for nearly 2,900 kilometers. The mantle is not a sea of magma. For the most part, it is solid, but it behaves in an unusual way. Under immense heat and pressure, the rock in the mantle can flow and deform over geological time, much like a glacier. This slow, creeping motion is what drives plate tectonics, moving continents, building mountains, and causing earthquakes. Our journey continues deeper, past the mantle, to the very heart of our world. At a depth of about 2,900 kilometers, we cross a boundary as sharp and defined as the surface of the planet itself, the core mantle boundary. Here, the world of rock ends, and a realm of metal begins. We have arrived at the Earth's core. The core itself is made of two distinct parts. In the very center is the inner core, a solid sphere of mostly iron and nickel, roughly the size of the Moon. The pressure here is almost incomprehensible, more than 3.5 million times the atmospheric pressure at sea level. This immense pressure is what forces the inner core to be solid, even though its temperature is staggering, estimated to be around 5,400 degrees Celsius, nearly as hot as the surface of the Sun. But it is the layer around the solid inner core that holds the key to our story. This is the outer core. And this is where we find our ocean. Stretching from a depth of about 2,900 kilometers down to 5,100 kilometers, the outer core is a vast, globe-spanning ocean of liquid metal. It has a volume more than 6 times that of the Moon, and it is composed almost entirely of molten iron and nickel. The pressures are still astronomical, but they are just low enough, and the temperatures just high enough, that the iron alloy remains liquid. Its viscosity is thought to be surprisingly low, more comparable to water than to the thick magma we often imagine. The temperature of this metallic ocean averages around 5,000 degrees Celsius. This is the planetary engine room. This turbulent, swirling, 5,000-degree ocean of liquid iron, 3,000 kilometers beneath our feet, is the source of the magnetic field. It is the birthplace of the invisible shield that protects all life on Earth. But how can a churning ball of liquid metal generate a planet-wide force field? The answer lies in a process known as the geodynamo. The engine room. How the geodynamo works. To generate a magnetic field, a dynamo requires 3 key ingredients. It turns out the center of our planet has all 3 in abundance. The first ingredient is an electrically conductive fluid. This is our ocean of liquid metal. The outer core, being made of iron and nickel, is an excellent conductor of electricity. Much like a copper wire allows electrons to flow through it, this vast sea of molten metal provides a medium for enormous electrical currents to move. The second ingredient is an energy source to put that fluid into motion. A stationary fluid will not generate a magnetic field, it must be moving. The energy source for the outer core is heat, which comes from 2 main places. First is the primordial heat left over from the planet's formation 4.5 billion years ago. Second, and more important for sustaining the dynamo, is the heat released as the inner core slowly grows. As the Earth gradually cools, iron from the liquid outer core crystallizes onto the surface of the solid inner core, which grows by about a millimeter a year. This process of crystallization releases latent heat, as well as lighter elements that don't fit into the solid iron structure. This combination of heat from below and cooling from above drives a powerful process called convection, much like a pot of water boiling on a stove. Liquid iron at the bottom of the outer core is heated, becomes less dense, and begins to rise. As these plumes of hot metal reach the top of the outer core, they lose heat to the cooler mantle, become denser, and sink back down. This creates massive, continuous, churning convection currents. But this churning motion alone is not enough. Randomly churning liquid would create only small, local magnetic fields that cancel each other out. The motion must be organized. This brings us to the third ingredient, planetary rotation. As the Earth spins on its axis, it imparts an organizing force on the moving liquid of the outer core, known as the Coriolis effect. This is the same force that deflects ocean currents and organizes weather systems into cyclones. In the outer core, the Coriolis force twists the rising and falling plumes of liquid iron into massive, spiraling columns, aligned roughly with the Earth's axis. Instead of random motion, there is now an organized, helical flow. When these 3 ingredients combine, a self-sustaining process begins. It starts with a weak, stray magnetic field, perhaps a remnant from the Earth's past or from the Sun. As the spiraling columns of conductive liquid iron move through this weak magnetic field, Faraday's law of induction dictates that an electric current is generated. Because the liquid iron is a fantastic conductor, this motion induces powerful electrical currents within those helical columns. Next, Ampere's law states that any electric current produces its own magnetic field. So, these new electrical currents, flowing in massive spirals, generate their own magnetic field. This creates a feedback loop that is both elegant and self-sustaining. Because the flow is organized into helical structures by the Coriolis force, the magnetic field it produces is also organized. It aligns with and reinforces the original magnetic field. This stronger field then interacts with the churning iron to create even stronger currents, which in turn generate an even stronger magnetic field. It is a self-exciting process that has been running for at least 3.5 billion years, converting the thermal and kinetic energy of the core into the immense magnetic energy of the magnetosphere. It is, in effect, a colossal, naturally occurring electromagnet at the center of our planet. A fickle protector. The geodynamo is a powerful engine, but it is not a perfectly steady one. It is a chaotic, turbulent system. As a result, our magnetic shield is in a constant state of flux. It weakens, it strengthens, it wanders, and on geological timescales, it can reverse its polarity. The first sign of this restlessness is the movement of the magnetic poles. The magnetic North Pole, the point a compass needle seeks, is not the same as the geographic North Pole. It is currently located in the Arctic Ocean, and it is moving. Since it was first located in 1831, it has drifted over 2,000 kilometers. In recent decades, this movement has accelerated from about 15 kilometers per year to around 55 kilometers per year, on a path from Canada toward Siberia. This wandering is a direct expression of the shifting fluid flows in the outer core. Another indication of the field's fluid nature is a gradual weakening in its overall strength. Since systematic measurements began in the 1830s, the field's total strength has declined by about 10%. This weakening is not uniform. There is a particularly large and growing area of weakness stretching from South America across the South Atlantic, known as the South Atlantic Anomaly. Here, the field is so weak that the Van Allen radiation belts dip closer to the surface, exposing satellites and spacecraft to higher levels of radiation that can disrupt their electronics. This anomaly is a clear indicator that the geodynamo is undergoing significant changes. These changes may be symptoms of the geodynamo's chaotic nature, but they may also be precursors to a more dramatic event, a geomagnetic reversal. By studying the magnetic signatures frozen into ancient volcanic rocks, geologists have learned that Earth's magnetic field has completely flipped its polarity hundreds of times. Magnetic north becomes magnetic south, and south becomes north. The last full reversal occurred about 780,000 years ago. Given that reversals have happened, on average, every 200,000 to 300,000 years, some scientists suggest we may be overdue for another. A reversal would not be an instantaneous switch. The process would likely take thousands of years. During this transition, the main dipole field, the simple north-south structure, would weaken significantly, perhaps to 10% of its current strength. The field would become far more complex, with multiple, temporary, north and south poles scattered across the globe. During this period, our planetary shield would be compromised. Radiation levels at the surface would increase. There is no evidence linking past reversals to mass extinctions, but such an event today would present a significant and unfamiliar challenge to our modern technological society. Power grids, satellites, and communication networks would all be far more vulnerable to solar storms. A reversal would not be an end to life on Earth, but it would be a profound geophysical event for modern civilization. Life under a magnetic sky. It is easy to think of the geodynamo as a purely geological process, but it is fundamentally intertwined with the story of life itself. The magnetic field is a prerequisite for the world we know. Let's return to the contrast with Mars. The red planet offers a quiet glimpse into what our world could have been. 4 billion years ago, Mars also likely had a geodynamo and a magnetic field. But because Mars is smaller, its core cooled more quickly, and its dynamo died. Without a magnetosphere, the solar wind stripped away its atmosphere and water, leaving it the frozen desert it is today. Earth retained its internal heat, its dynamo kept churning, and its magnetic field held. This shield allowed our planet to hold onto its atmosphere and its oceans. It created the stable, protected environment where life could not only emerge but evolve over billions of years. The magnetic field also shields life from galactic cosmic rays, high-energy particles from distant supernovae that can damage DNA. Our magnetic field and atmosphere work together to deflect the vast majority of these particles. And while we cannot perceive the magnetic field, for countless other species, it is a tangible part of their sensory world. The study of magnetoreception has revealed that an incredible variety of animals use the Earth's field for navigation. Migratory birds possess a magnetic compass, allowing them to travel vast distances. Sea turtles use the field not just as a compass, but as a map, sensing subtle variations in its strength to determine their geographic position and return to the beaches where they were born. For much of the animal kingdom, the geodynamo provides an invisible network of navigational beacons. For humans, our reliance is more modern but no less profound. For centuries, the magnetic compass allowed for global exploration. Today, our technological infrastructure depends on the stability the field provides. GPS satellites, which form the backbone of modern navigation and logistics, are vulnerable to the very radiation the magnetosphere protects them from. From the air we breathe to the map on our phones, our existence is tied to this invisible force. It is an unsung hero in the story of life on Earth, a story made possible by the quiet, chaotic physics churning in the planet's deep interior. The surface of our planet feels stable, permanent. But we know this perception of stillness is maintained by an engine of immense scale and force, deep within the Earth. 3,000 kilometers down, an ocean of liquid iron churns at 5,000 degrees. It is a turbulent, self-sustaining dynamo, a remnant of our planet's formation, converting heat and motion into a vast, life-sustaining force field. This shield wages a constant, silent war against the radiation of space, protecting our atmosphere, our water, and our DNA. The next time you look up at the sky, or feel the warmth of the sun, it is worth remembering what is happening below. Remember the 5,000-degree ocean of metal, larger than a planet, swirling in the darkness. Remember the silent guardian it generates, a shield forged in the very heart of our world, that is protecting all life on Earth. If this kind of calm exploration into the world helps you unwind, consider liking the video and subscribing to the channel. And for another deep dive into the forces that shape our world, you can find our video right here on what would really happen if the Earth suddenly stopped spinning. Earth's invisible shield is weakening. What happens next? For billions of years, an invisible force field has quietly wrapped around our world. It is a silent guardian, a shield generated by the very heart of the planet. This magnetic field is the single most important barrier protecting all life on Earth from the steady flow of cosmic radiation and the sun's energetic winds. Without it, our atmosphere would be slowly stripped away, the oceans would eventually disappear into space, and the surface would become a quiet, barren rock. For eons, it has held strong, a steadfast protector in a vast cosmos. But now, that is beginning to change. Scientists have noticed something subtle, but significant. Our planetary shield is weakening. A vast, mysterious dent in this shield is growing larger and deeper, and we are only just beginning to understand the consequences. We are seeing the first signs of what might happen if it were to weaken further. What follows is not a prediction, but an exploration of the events that could unfold, from a technological disruption that could quiet our modern world, to the day Earth itself begins the long, slow journey toward becoming a barren, inhospitable world, much like Mars. What is this shield? Why is it changing? And what might happen next? To understand the change, we must first understand the shield itself. Imagine the Earth not as a solid, inert rock, but as a dynamic engine. Deep beneath our feet, nearly 3,000 kilometers down, lies the outer core. It is a turbulent, global ocean of liquid iron and nickel, reaching temperatures comparable to the surface of the Sun, churning in massive, slow-moving currents. The heat from the solid inner core causes this molten metal to rise, cool, and sink, creating vast, powerful flows. Now, add the planet's rotation. The spin of the Earth twists these colossal flows of molten metal into immense, spiraling columns. This is the geodynamo. It functions something like a bicycle dynamo on a planetary scale. The movement of a conductive material, in this case, liquid iron, generates powerful electrical currents. These currents, in turn, generate our planet's immense magnetic field. It is a self-sustaining loop, but one that is incredibly complex and, at times, chaotic. Without the molten core, or without the planet's rotation, this protective field would simply fade away. Visually, this field resembles that of a simple bar magnet, with a north and a south pole. These magnetic poles are tilted about 11 degrees from Earth's rotational axis, which is why a compass doesn't point to the true geographic North Pole. Field lines loop out from the southern magnetic pole, arc through space, and plunge back down at the northern magnetic pole, forming a vast, invisible bubble around our planet called the magnetosphere. On the side of Earth facing the Sun, this bubble is compressed by the constant pressure of the solar wind. On the night side, it's stretched out into a long tail, like a windsock in a gentle breeze. This bubble is our first line of defense. It deflects the vast majority of charged particles that stream from the Sun. So why can't we feel it? Why can't we see this monumental shield that shapes our existence? The reason is that its force, while planetary in scale, is incredibly diffuse at the surface, far too faint for our senses to detect. And yet, its presence is written all around us, if you know where to look. It is what guides a simple compass. It is the invisible map used by countless migratory species. Birds, sea turtles, and even some bacteria have a built-in sense called magnetoreception, allowing them to perceive the field and navigate the globe with quiet precision. And, most spectacularly, we can see the field in action during the aurora. When solar storms buffet our magnetosphere, some particles are funneled down the field lines near the poles. As they collide with gases in our upper atmosphere, they release energy as light, creating the shimmering curtains of the northern and southern lights, a beautiful and visceral reminder of the cosmic forces at play above our heads. The greatest proof of our shield's importance is found not on Earth, but 400 million kilometers away, on the quiet, red surface of Mars. The story of Mars is a cautionary tale, a glimpse into a potential future for a world that loses its magnetic protection. Billions of years ago, Mars was a different world. It had a thicker atmosphere and flowing liquid water. It may have had the right conditions for life. Like Earth, early Mars had a molten core that generated a protective magnetic field. But Mars is smaller than Earth. Its internal engine cooled and solidified much faster. As the Martian core grew cold, the geodynamo sputtered and died. The planet's magnetic shield vanished. Without that shield, the solar wind slammed directly into the Martian atmosphere. Over millions of years, this steady bombardment stripped the atmosphere away, particle by particle. As the atmosphere thinned, the air pressure plummeted. The liquid water on the surface either boiled away into space or froze solid. Today, Mars is a cold, barren desert, with an atmosphere less than 1% as thick as Earth's. Its surface is exposed to deadly levels of solar and cosmic radiation. The journey from a potentially habitable, water-rich world to a sterile, frozen wasteland was set in motion by one critical event: the death of its magnetic field. Our shield does more than protect our atmosphere. It deflects the most energetic cosmic rays, particles that can damage DNA. The field also helps protect our planet's ozone layer, our primary defense against the sun's harmful ultraviolet radiation. This protection is not abstract, it affects the technology we rely on. GPS satellites, power grids, and even our own health at high altitudes are all quietly shielded by this invisible force. It has created a safe haven, a gentle cradle in a sometimes violent universe, allowing our atmosphere, our oceans, our technology, and our biology to flourish. This protector is now showing signs of change. For the past 2 centuries, scientists have measured the strength of the Earth's magnetic field with increasing precision. The data reveals a subtle trend. On average, the global magnetic field has weakened by roughly 9%. This weakening is not uniform. In one vast region, the decay is happening at a more noticeable rate. This region is known as the South Atlantic Anomaly. It is a huge, sprawling dent in our magnetic armor, stretching from South America toward Africa. Inside this anomaly, the magnetic field is significantly weaker than anywhere else on Earth. This is not a new phenomenon, but what is interesting is its recent behavior. Data from the European Space Agency's swarm satellites has given us a clearer picture. The South Atlantic Anomaly has expanded, and it appears to be splitting into 2 distinct lobes, or cells of minimum strength. One is centered over South America, while a second, more rapidly weakening lobe has developed southwest of Africa. As Professor Chris Finlay of the Technical University of Denmark noted, the South Atlantic Anomaly is not just a single block. It's changing differently towards Africa than it is near South America. There's something special happening in this region that is causing the field to weaken in a more intense way. The consequences of this weak spot are not theoretical, they are happening now. The South Atlantic Anomaly is a region where the Van Allen radiation belts, rings of energetic particles trapped by our field, dip closer to the surface. Any satellite passing through this region is exposed to a higher dose of particle radiation. This can cause software glitches and damage sensitive hardware. The problem is so well known that operators of satellites, including the Hubble Space Telescope, often power down sensitive instruments when passing through the anomaly to avoid damage. In March 2016, Japan's Hitomi X-ray Observatory was lost after it passed through this region. The mission's failure was ultimately caused by a software error that sent it into an uncontrollable spin, a catastrophic failure in a zone known to be hazardous for spacecraft. As the anomaly grows, these risks increase. The Bermuda Triangle of space, as some have called it, is expanding, posing a quiet, persistent challenge to the orbital infrastructure that supports our global communication and navigation systems. The cracks in the shield are real, they are growing, and they are a quiet warning of the much larger processes unfolding deep within the Earth. The weakening we see today may be a symptom of a much larger planetary process, a geomagnetic reversal. The Earth's magnetic field is not static. Throughout geological history, it has flipped hundreds of times. The last full reversal occurred about 780,000 years ago. We know from studying magnetized rock layers that these reversals are not instant. They are messy, complex affairs that can take thousands of years. During a reversal, the main dipole field, the simple north-south structure, decays significantly, perhaps to as little as 10% of its current strength. Multiple, weaker magnetic poles can appear in random locations. A compass would become useless, its needle spinning erratically. While geologists assure us that a reversal is a slow process on a human timescale, The path to that reversal would be marked by disruptions to our technologically dependent world. Let's explore a hypothetical journey of what could happen as the shield continues to change. The first phase would be subtle. As the field weakens, its ability to shield us from the sun's activity diminishes. Geomagnetic storms would have a greater impact. The first, most beautiful sign would be in the sky. The aurora, normally confined to high latitudes, could become a more common sight across the globe. Shimmering curtains of light might be seen from places they are rarely visible, a magnificent, but telling, spectacle. At the same time, the issues with our satellite infrastructure would grow. GPS inaccuracies could become more common, causing disruptions for aviation and logistics. For most people, it would be an era of growing inconvenience. Your phone's map might be less reliable, or the internet might drop out during a solar storm. It would be the first tremor, a quiet sign of the planet's deep, internal changes. As the reversal process continued over centuries, the main dipole field would collapse into a more chaotic state. This is where the most serious consequences for modern civilization lie. Our orbital infrastructure would become increasingly difficult to maintain. The constant bombardment of high-energy particles would shorten the lifespan of satellites, making global communications and GPS navigation unreliable. The most significant impact would be on our electrical grids. Our planet would be left more vulnerable to a major solar storm, a superstorm like the one that struck in 1859. Back then, it only affected telegraphs. Today, a similar storm striking a significantly weakened magnetic shield would induce powerful currents into our grids. These currents could overwhelm and damage the large transformers that are the backbone of the system. The result could be a cascading blackout on a continental scale. And this would not be a short-term problem. These large transformers are difficult and time-consuming to build and replace. A widespread failure could lead to blackouts lasting for months or even years. The consequences of a world without electricity are profound. No clean water being pumped, no refrigeration, no modern healthcare, no digital economy. It would be a quiet, slow-motion collapse of the intricate systems that support modern life. At the same time, radiation levels would increase, particularly at high altitudes, likely ending commercial air travel as we know it. At the peak of the reversal, a process that could last for centuries, the Earth would be a different planet. The night sky might shimmer with a perpetual, global aurora, a visible sign of our atmosphere being bombarded. The process of atmospheric stripping, the one that turned Mars into a wasteland, would begin, but this is a process that takes millions of years. The reversal would simply be the trigger for a change that would unfold on a geological timescale. The world of our distant descendants would be different, shaped by forces that began moving in our time. So, is it time to panic? The scientific consensus is no. While the weakening is real, we are not on the brink of an imminent reversal. These processes unfold over geological time, likely taking many centuries or millennia. Life on Earth has survived hundreds of these reversals before, and there is no evidence in the fossil record linking them to mass extinctions. But there is a crucial difference between then and now. Previous life on Earth did not depend on a fragile, globally interconnected technological civilization. The single greatest threat of a magnetic field collapse is not to life itself, but to our modern way of life. The science of our magnetic field is constantly evolving, with missions like the ESA's Swarm constellation giving us an unprecedented look into the heart of our planet. If this kind of calm exploration into the forces that shape our world helps you unwind, consider liking the video and subscribing to the channel. And let us know in the comments, what part of our quiet reliance on the magnetic field surprises you the most? The weakening of our invisible shield is a profound reminder of our place in the cosmos. We live on a planet with immense and sometimes unpredictable powers. We are protected by a force we cannot see or feel, yet our entire modern existence depends on it. The next time you see a compass needle point north, or catch a glimpse of the aurora, remember the turbulent ocean of liquid iron 3,000 kilometers beneath your feet, and the silent guardian it generates. It has protected life for eons. The challenge for humanity will be learning to live in a world where that protection may, very slowly, begin to falter. Why Earth is alive and Mars is a dead planet. One planet is a familiar, living world. A soft blue marble in the dark, covered in oceans and wrapped in a thick atmosphere. The other is a quiet, frozen desert. A red world where the only sound is a thin wind moving over dust that has long since forgotten the feeling of water. They began as siblings, born from the same cosmic material, orbiting the same star. For a time, they seemed to walk a similar path. Both had oceans. Both had atmospheres. Both, perhaps, held the quiet potential for life to begin. But one of them lost its invisible shield. And in that moment, its long future was decided. This is a story of two worlds, two very different outcomes, and a single, planetary change. It is the story of how Mars became a fossil of its former self, and why an invisible field around the Earth is the only thing that keeps our world from the same fate. If this kind of calm exploration into our planet's story helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share where you're watching or listening from. There is an unseen process happening right now, all around you. A constant and invisible stream of charged particles is sent out from the sun, moving at over 1,000,000 miles per hour. This is the solar wind. It is a force that has the energy to slowly strip a planet of its air, to wear away its oceans, until only sterile dust is left. And yet, here on the surface, we feel nothing. We are protected by something we cannot see or touch, something we rarely think about. A silent guardian is turning this cosmic storm away, and it is saving our world, every second. To understand how important this protection is, we only need to look at our neighbor, Mars. It, too, was once a world of possibilities. We can read its history in the landscape, and the evidence is overwhelming. We see ancient, dried-up river valleys, deltas, and the beds of vast lakes. For a time, water flowed across the Martian surface. The planet had a thicker atmosphere, a warmer climate, and the ingredients thought to be necessary for life. But billions of years ago, Mars lost something fundamental, its protective shield. Without that shield, the solar wind began to wear away at the planet. Slowly, particle by particle, over millions of years, it stripped the Martian atmosphere away. The air became too thin to hold warmth, or to keep water in its liquid state. Today, Mars is a frozen desert, a quiet monument to a world that could have been. Earth did not follow this path. We are here today because our planet has something Mars lost, an invisible, life-sustaining force field. But what if it were to slowly fade away? The story of what would follow is not just a thought experiment. It's the true story of why we are here, and Mars is not. A world blinded and broken. Imagine a world where every compass becomes useless. Not just the old ones, but the digital compass in every phone, car, and airplane. They wouldn't just be a little off. They would be lost, spinning without direction, or freezing in place. This would be the first quiet sign that Earth's magnetic field had vanished. It would be the subtle warning for a civilization about to be disconnected. Soon, the real consequences would begin. High above us, the thousands of satellites that our modern world depends on would be moving through a storm of radiation. Earth's magnetic field, our magnetosphere, acts as a shield, deflecting the most energetic particles from the sun. Without it, this radiation would strike the delicate electronics of our satellites directly. GPS would fail. Global communications would be severed. Weather forecasting would become a process of guesswork. The network of data that runs financial markets, logistics, and emergency services would slowly unravel. Airplanes in mid-flight would lose their most reliable navigation tools. forced to rely on older methods in skies that were suddenly unfamiliar. But the most visible effects would appear across the entire globe. The solar wind, no longer held back, would pour into our upper atmosphere. The auroras, those beautiful displays of light normally found only near the poles, would erupt everywhere. The sky, in every country, would light up in a constant, shimmering display of green, purple, and red. It would be a beautiful symptom of a planet growing unwell. This light show, however, would come with a cost. As these high-energy particles entered the atmosphere, they would create powerful electrical currents. These currents would, in turn, cause surges in our electrical grids on the ground. Transformers would overload. Power stations would fail. Entire continents would go dark. It wouldn't be a temporary blackout, but a slow and cascading failure of the electrical systems that power modern life. And then there is the radiation. The magnetic field and the atmosphere work together to protect us from solar radiation and cosmic rays. Without the field, that first line of defense is gone. Radiation levels on the surface would begin to rise. While not immediately lethal, anyone in a high-altitude airplane or living in a high-altitude city would receive a much larger dose. For astronauts on the International Space Station, the situation would be far more serious. They would be exposed to such high levels of radiation that any mission would have to end, but even returning would be dangerous. They would see the Earth below them wrapped in a global, unending aurora, a sign that the shield that protected them, and all of us, was gone. In a short time, our technological world would be broken. We would be disconnected and in the dark. But this is only the beginning. These short-term effects, as serious as they are small compared to the slow, quiet transformation that would follow. The planet itself would begin to change. The planetary engine. The secret of the shield. To understand why this invisible shield exists, we have to travel to the center of our planet. The secret to Earth's protection is not on its surface, but thousands of kilometers beneath our feet, in the planet's core. The Earth's core has two parts. A solid inner core made of iron and nickel, about the size of the Moon, and a liquid outer core that surrounds it. This outer core is a vast ocean of molten iron and nickel, under immense pressure. It is this ocean of liquid metal that generates our planet's magnetic field, through a process known as the geodynamo. It can be thought of as a planet-sized generator, and it requires three things to work. First, a conductive fluid. The molten iron nickel of the outer core is an excellent electrical conductor. Second, motion. Heat flows out from the solidifying inner core, creating powerful convection currents in the liquid metal, like water boiling in a pot. Third, spin. As the Earth rotates, the Coriolis effect, the same force that puts the spin in hurricanes, organizes these churning currents into massive, spiraling columns. This is where the process becomes self-sustaining. As these rotating columns of conductive molten metal move, they generate powerful electrical currents. And any electrical current generates a magnetic field. These fields, in turn, influence the flow of the molten metal, which then generates more current. It's a feedback loop of immense scale that has been running for billions of years, turning the thermal and rotational energy of our planet into a vast magnetic field. This field extends far into space, wrapping the Earth in an invisible bubble called the magnetosphere. It is our primary shield against the solar wind. When the solar wind, a stream of charged particles, hits the magnetosphere, the field deflects most of them, forcing them to flow around our planet like water around the bow of a ship. The magnetosphere is not just a simple barrier. Some particles from the solar wind become trapped by the magnetic field lines, creating two donut-shaped zones of intense radiation around the Earth, known as the Van Allen belts. These belts hold high-energy particles, preventing them from reaching the surface. The auroras we see are a quiet reminder of this process, particles guided by the magnetic field toward the poles, where they collide with atoms in our atmosphere and release their energy as light. This entire system, the geodynamo generating the magnetosphere, which deflects the solar wind, is the reason Earth has a thick atmosphere, liquid oceans, and life. It is the fundamental difference between a living world and a dead one. It is the planetary engine that, on Mars, eventually fell silent. The slow death, stripping a world bare. If the magnetic shield were gone, the first effects would be technological. But the years, centuries, and millennia that would follow would bring a slow, methodical change to the planet itself. The process is known as atmospheric stripping, and it is driven by the Sun. Without the magnetosphere, the solar wind would directly hit the upper layers of our atmosphere. This is not a gentle process, it's a high-energy bombardment. One of the main ways it strips atmosphere away is called sputtering. You can think of it like a sandblaster, where high-energy particles from the Sun collide with atoms of air and knock them out into space. Lighter gases like hydrogen and helium would go first, but over time, heavier gases like nitrogen and oxygen would be lost as well. NASA's MAVEN mission at Mars measured this exact process and found it was responsible for stripping away much of the Martian atmosphere. Another method is driven by the Sun's intense ultraviolet radiation. High-energy photons would break apart molecules in the air. Water vapor would be split into hydrogen and oxygen. Hydrogen, the lightest element, would escape into space almost immediately. This is how a planet loses its water. It isn't simply boiled away, it is chemically taken apart and carried off, piece by piece, into space. Over decades and centuries, the ozone layer would be the first major casualty. This layer in our stratosphere absorbs most of the Sun's harmful ultraviolet radiation. Without the magnetic field's protection, charged particles would help erode this layer much faster than it could be replenished. Lethal levels of UV radiation would reach the surface, sterilizing the land and the upper layers of the ocean. Life would be forced to retreat deep underground or into the darkest parts of the sea to survive. As the atmosphere continued to thin, the planet would lose its ability to hold onto heat. The greenhouse effect would weaken and the Earth would begin to cool. At the same time, with less air pressure, the boiling point of water would drop. Eventually, the pressure would become so low that the oceans would begin to boil, not from heat, but from the lack of pressure holding them in a liquid state. This would send a great deal of water vapor into the atmosphere, which would then also be broken apart and stripped away by the solar wind. Over thousands of years, the Earth would transform. The blue sky would become thin and pale, eventually turning a dusty pink, like the sky on Mars. The oceans would vanish, leaving behind empty basins crusted with salt. The surface, bombarded by unfiltered radiation, would become a sterile, frozen desert. The living blue marble would become a silent, red rock. This isn't just speculation. This story is written in the geology of our nearest planetary neighbor. The world we have just described is Mars. This is what happens when a planet's internal engine stops working. The ghost of a world, the Martian autopsy. For centuries, Mars was a point of light in the sky. Today, thanks to orbiters, landers, and rovers, we can read its history in the rocks and dust. That history tells a quiet and clear story. Mars was once a world much more like Earth. The evidence is written across its surface. We see vast, dried-up river valleys that stretch for hundreds of kilometers. Rovers like Curiosity and Perseverance have driven through ancient lake beds and river deltas, analyzing rocks that could only have been formed in the presence of water. Mars did not just have a little water. It may have once had a shallow ocean in its northern hemisphere. To support liquid water, Mars must have had a much thicker atmosphere to trap heat. And to have a thick atmosphere for a long time, it must have had a global magnetic field. And it did. Data from spacecraft like the Mars Global Surveyor found the ghost of this ancient field. Today, Mars has no global field, but it does have pockets of strong magnetic fields locked into its crust, especially in the older southern highlands. These are fossil magnets, remnants of a time when Mars had a working geodynamo, just like Earth's. The age of these rocks tells us the dynamo was active when the rivers and lakes were forming. Then, around 4 billion years ago, the Martian dynamo wound down. The planet's heart stopped. The leading theory is that this was a consequence of size. Mars is a smaller world than Earth, with about half its diameter and only about a tenth of its mass. Being smaller, it cooled down more quickly after it formed. Earth's larger, hotter core has remained partly liquid, allowing the geodynamo to run for billions of years. Mars's smaller core likely cooled and solidified much faster. As the churning in its liquid outer core slowed and stopped, the geodynamo died. Once the magnetic field vanished, the solar wind was free to interact directly with the Martian atmosphere. With its weaker gravity and no shield, Mars was vulnerable. The stripping process began. The MAVEN spacecraft has measured the rate at which Mars is still losing its thin atmosphere today, and it confirmed that the solar wind is the primary cause. Billions of years ago, when the Sun was younger and more active, this process would have been much more intense. As the atmosphere thinned, the pressure dropped. The water on the surface either evaporated and was lost to space, or it froze into the polar ice caps and underground permafrost we see today. The planet that was once warm and wet became cold, dry, and empty. The autopsy of Mars points to a clear cause of death: the failure of its internal engine, the loss of its magnetic shield, and a slow erosion by the solar wind. Mars stands as a quiet, planetary-sized reminder of what happens when a world loses its protection. A living shield. The nuances of our guardian. Earth's magnetic field is more than a simple barrier. It is a complex and dynamic system. We often picture it as a perfect bubble, but its shape is constantly molded by the solar wind. On the side facing the Sun, it is compressed. On the night side, it is stretched out into a long tail, like a windsock showing the direction of the solar gale. And this shield is not perfect. It traps particles in the Van Allen radiation belts, a clear reminder of the radiation it protects us from. Satellites and astronauts must pass through these belts carefully to minimize exposure. The field also touches life on Earth in more subtle ways. Many animals have an ability called magnetoreception, the sense of the Earth's magnetic field. Migratory birds, sea turtles, and salmon use the field as a natural compass for their long journeys. Some scientists believe that for certain birds, the magnetic field may be something they can actually see, superimposed on their normal vision. It shows that the field is not just an external shield, it is part of the environment that life has learned to use. But this vital field is not static. It is always changing. Scientists are monitoring a large area of weakness known as the South Atlantic Anomaly, stretching from South America to southern Africa. Here, the field is so weak that satellites passing through are more exposed to radiation. This spot has been growing and changing, a sign of the complex movements in the Earth's core far below. At the same time, the magnetic North Pole is moving. After centuries of being relatively stable in the Canadian Arctic, its pace has recently quickened as it races toward Siberia. This forces regular updates to navigation systems all over the world. This weakening and shifting has led some to wonder about an impending magnetic pole reversal, where north and south would flip. It's important to be clear: a reversal is not the same as a disappearance. The geologic record shows this has happened hundreds of times in Earth's history, but it is not an instant event. The process can take thousands of years. During that time, the main field would weaken and become more complex, with multiple smaller poles appearing across the globe. Our planet would be less protected, but it would not be defenseless. Most scientists believe the current changes are simply fluctuations, not the start of a full reversal. The shield is dynamic. It ebbs and flows, shifts and changes. It is not a perfect, static force field, but a living part of our planet's machinery, in a constant dance between the deep core and the distant Sun. In the story of our solar system, the line between a living world and a dead one can be very subtle. Two planets, Earth and Mars, began as siblings, both blessed with water and air, the raw materials for life. But one was given a gift that would last: a persistent internal engine generating an invisible shield. The other's engine failed, and its shield faded, leaving it exposed to the quiet, relentless force of its own star. Every day, that invisible shield, our magnetic field, performs a quiet and profound function. It is the guardian that stands between our living, blue world and the cold, silent fate of Mars. It turns away a storm we cannot see, protects an atmosphere we take for granted, and helps hold onto the oceans that gave rise to life. The story of Mars is not just a cautionary tale. It gives us a sense of perspective. It shows us that a planet's habitability is not a given, but a fragile state maintained by a quiet balance of powerful forces. We live on a world that is not just a rock in space, but a dynamic, interconnected system. It is, in a very real sense, alive. And its life is what allows for ours. The next time you look up at the blue sky, you can remember the invisible battle being fought for it, thousands of kilometers above your head. You can remember the silent, churning heart of our world. And you can remember the ghost of a planet next door, a quiet reminder of how fortunate we are. Earth's invisible shield is weakening and scientists are worried. Suspended in the silent, black expanse of space, our planet looks like a serene, blue marble. A haven of impossible life, peaceful and complete. But this tranquility is a carefully maintained balance. Every moment, Earth is in a quiet, constant dialogue with the Sun. It is met by a relentless stream of energetic particles, a cosmic flow that, if left unanswered, would slowly sterilize our world, break down our oceans, and strip our atmosphere away into space. What stands between us and that outcome is something you can't see, taste, or touch. An invisible field, generated by the churning heart of the world itself. It is our planet's quiet guardian. But new data suggests this shield is changing. For reasons we are only just beginning to understand, it appears to be weakening. In one vast region, an area of unusual thinness is forming, a measurable, growing difference in our line of defense. This is the story of our planet's magnetic field, the patient effort to understand what happens when that defense begins to change, and what it means for the world we know. If this kind of calm exploration into the forces that shape our world helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share where you're watching or listening from. The quiet guardian. What is the magnetic field? Before we explore the change, we must first journey to the heart of the planet. What is this invisible force that has shaped the destiny of life on Earth? For most of human history, its only tangible evidence was a curious little needle in a compass. That small sliver of metal, always pointing north, allowed us to navigate the vast oceans, to map our world, and to build the global civilization we know today. Your phone's map app, the guidance systems in every airplane, they all rely on this ancient, planetary secret. They are all speaking to the Earth's magnetic field. But this field is so much more than a navigational tool. It is a guardian. To understand it, you have to picture what's happening 3,000 kilometers beneath your feet. Below the crust and the thick, rocky mantle lies the Earth's core. The very center is a solid ball of iron and nickel, held in place by immense pressure. Surrounding that solid inner core is a vast, turbulent ocean of the same metals, in a liquid state. It is a realm of slow, powerful motion, a swirling, roiling sea of molten metal with temperatures that can reach up to 6,000 Kelvin. This is the engine room of our planet. As the Earth spins on its axis, it drags this metallic ocean with it. Heat escaping from the inner core causes the liquid metal to churn in massive, corkscrewing columns, like water boiling in a pot the size of a planet. This colossal movement of molten iron, a conductive fluid, generates immense electrical currents. It is a process known as the geodynamo, and it turns the core of our planet into a gigantic electromagnet. These currents, in turn, produce the magnetic field, a planetary force that envelops our world. Imagine a simple bar magnet. It has a north and a south pole, with invisible lines of force looping from one to the other. Earth's magnetic field is similar, but far more complex and dynamic. It emerges from the southern hemisphere, wraps around the planet in a great, sweeping arc, and re-enters in the northern hemisphere. The points where these field lines converge are our magnetic poles. It's important to note that these are not the same as the geographic north and south poles, the fixed points of Earth's rotation. The magnetic poles are restless. They wander. Currently, the magnetic North Pole is located about 10 degrees away from the geographic north, and as we will see, its movement has recently become unusually fast. This entire structure is a product of planetary physics, a delicate dance of heat, pressure, and motion on a scale that is almost impossible to comprehend. For billions of years, this churning, molten heart has been the silent architect of our world's survival, creating a shield that extends tens of thousands of kilometers out into space. A shield that is now being studied more closely than ever. So, what exactly is it protecting us from? To understand that, we need to look 93 million miles away, to the star that gives us life, and also releases the very particles our planet must deflect. The cosmic deflection, the magnetosphere in action. Our sun is not a gentle, benevolent star. It is a nuclear furnace, constantly releasing a stream of its own substance out into the solar system. This is the solar wind. It's not a wind in any terrestrial sense. It's a superheated plasma, a flow of charged particles, mostly protons and electrons, moving away from the sun in all directions at more than 1 million miles per hour. This is a persistent flow of radiation that would, over immense spans of time, erode any unprotected planet in its path. Without a defense, the solar wind would interact with the gases in our upper atmosphere and slowly strip them away, molecule by molecule. Our air would bleed out into space. The water in our oceans would be broken down by solar radiation, its components vanishing too. Earth could become a barren, desolate rock, perhaps much like its neighbor, Mars. Mars, scientists believe, may have once had a thicker atmosphere and liquid water. It might have held the potential for life. But early in its history, its internal dynamo appears to have shut down. Its magnetic field faded. Without that shield, the solar wind has washed over the planet for billions of years, leaving behind the cold, arid, and nearly airless world we see today. Mars is a ghost planet, a quiet reminder of what happens when a world loses its shield. This is the fate our own planet avoids, thanks to the magnetosphere. The magnetosphere is the region of space dominated by Earth's magnetic field. It's our shield in action. As the solar wind moves towards us, it first encounters this invisible barrier. The magnetic field acts like a rock in a supersonic stream, deflecting the vast majority of those particles, forcing them to flow around our planet instead of impacting it directly. The side of the magnetosphere facing the sun is compressed by this constant pressure, forming a curved boundary known as the bow shock, which stands about 60,000 kilometers from Earth. On the opposite side, the night side, the field is stretched out by the solar wind into a long, trailing magnetotail, extending for millions of kilometers, far beyond the orbit of the Moon. But the shield is not entirely impenetrable. Some solar particles become trapped within the magnetic field, spiraling along the looping field lines. They are funneled down towards the magnetic poles, where the field lines converge and enter the Earth. As these energetic particles descend, they finally collide with molecules of oxygen and nitrogen in our upper atmosphere. When they do, something beautiful happens. The collisions excite those atmospheric gases, causing them to glow. The result is one of the most spectacular natural displays on Earth, the aurora borealis and aurora australis. The northern and southern lights are the visible evidence of our planet's magnetic shield in its constant, quiet interaction with the sun. They are a gentle reminder that we live within a protective bubble, a safe harbor in the energetic environment of space. For all of human existence, this shield has held. It has bent, it has flexed, it has shimmered with auroral light, but it has not broken. New, incredibly precise measurements, however, are telling us a new story. The shield has a region of weakness. And that region is growing. A region of weakness, the South Atlantic Anomaly. For decades, space agencies have been aware of an unusual region in near-Earth orbit. A place where their satellites would sometimes glitch, where instruments would return faulty data. Astronauts passing through this zone reported seeing strange flashes of light inside their closed eyes, the result of high-energy cosmic rays striking their retinas. This quiet, invisible region has a name: the South Atlantic Anomaly. The South Atlantic Anomaly, or SAW, is a vast area stretching from South America across the Atlantic towards southern Africa, where the Earth's magnetic field is unusually weak. Think of the magnetic field as a protective shell. In this one enormous region, there is a deep and growing depression. The field strength here is significantly lower than the global average. In this weakened zone, the protection offered by the magnetosphere is reduced. The inner Van Allen radiation belt, a band of highly energetic particles trapped by our magnetic field, dips closest to the Earth's surface, right over the SAW. Instead of being tens of thousands of kilometers up, this hazardous radiation is just a few hundred kilometers above the ground. For anything in low Earth orbit, passing through the SAW is like flying through a persistent radiation storm. Satellites are particularly vulnerable. When they enter the anomaly, they are exposed to a higher flux of high-energy protons that can interfere with their electronics. This can cause single-event upsets, where a particle strikes a microchip and flips a bit from a 0 to a 1, corrupting data or causing a software error. In some cases, it can cause permanent damage to components. Operators of the Hubble Space Telescope, for instance, power down some of its sensitive instruments when it passes through the anomaly to prevent damage. The International Space Station is also affected. Its path takes it through the SAW regularly, exposing astronauts to higher doses of radiation, a concern for their long-term health. The most interesting part is that the latest data, primarily from the European Space Agency's swarm satellites, shows that the South Atlantic Anomaly is not static. It is growing and changing. Since 2014, the anomaly has continued to expand westward at a pace of about 20 kilometers, or 12 miles, per year. Even more curiously, the SWARM mission has revealed that the anomaly may be splitting into two distinct lobes. A new, second center of intense weakness has developed southwest of Africa, and it seems to be deepening. So what is causing this? Scientists believe the SAW is not a surface phenomenon. Its origins lie deep within the planet, in the slow, churning motion of the liquid outer core. The geodynamo is not a perfectly smooth and symmetrical engine. Researchers theorize that there are massive, dense structures at the boundary between the core and the mantle, which may be disrupting the flow of the molten iron above them. It's thought that under the South Atlantic, a patch of the magnetic field is actually reversed. The field lines, instead of looping out into space, are being pulled back into the core in the wrong direction. This creates a localized area of profound weakness at the surface. The growth and splitting of the SAW likely signal a major, ongoing disturbance in the Earth's deep interior. It is a surface symptom of a much deeper planetary process. The South Atlantic Anomaly is the most dramatic evidence of our shield's changing nature, but it's not the only sign that something is different. When we zoom out and look at the magnetic field as a whole, the picture becomes even more complex. A global shift, a weakening field, and the wandering poles. The changes are not confined to the South Atlantic. Globally, our planet's magnetic shield appears to be losing some of its strength. By comparing modern satellite measurements with historical records from ships and magnetic observatories, scientists have calculated that in the last 200 years, the Earth's magnetic field has weakened by an average of about 9%. The current rate of decay is estimated to be around 5% per century. This is a significant and rapid decline in geological terms. This global weakening is not uniform. Data from the ESA's swarm satellites has allowed scientists to create a high-resolution map of the changes. It shows a fascinating pattern. While the field over the Americas and the Atlantic is weakening, other areas are actually getting stronger. There are two competing strong points in the Northern Hemisphere, one over Canada and one over Siberia. The balance between them is shifting. In recent years, the magnetic region over Canada has weakened, while the patch over Siberia has grown stronger. This shifting balance deep within the planet is having a very noticeable effect on the surface. The magnetic North Pole is moving, and its pace has quickened. For over a century after its location was first confirmed in 1831, the magnetic North Pole drifted slowly, at about 15 kilometers or 9 miles per year. But in the 1990s, something changed. It began to accelerate. Its speed increased to around 55 kilometers per year, or about 34 miles per year, as it moved away from the Canadian Arctic towards Siberia. This rapid movement has had real-world consequences. The World Magnetic Model, WMM, is the mathematical representation of the Earth's field that is the foundation for modern navigation, used by governments, airlines, and even the operating system of your smartphone. The pole was moving so fast that the 2015 version of the model became inaccurate sooner than expected. In 2019, scientists had to issue an unprecedented out-of-cycle update to prevent navigational errors. The latest data indicates that the pole's rapid movement has slowed somewhat, to about 40 kilometers per year, but its journey towards Russia continues. We are now in a situation where the magnetic patch over Siberia is strengthening, pulling the pole in its direction, while the opposing patch over Canada weakens, losing its grip. This dynamic dance between two colossal magnetic blobs in the Earth's core is redrawing our maps in real time. A weakening global field, a growing anomaly, and a magnetic pole that is migrating at a historically unusual speed. When scientists put all of this evidence together, it points towards one large-scale question. Is this all a prelude to something even bigger? Is our planet's magnetic field preparing to reverse? The ultimate reset? Is a pole reversal coming? The evidence is subtle but points to a pattern. A weakening shield, a growing anomaly, and wandering poles. Many geophysicists believe they could all be symptoms of a single, massive planetary process. A full geomagnetic reversal. A pole flip. This means exactly what it sounds like. The magnetic North Pole becomes the magnetic South Pole, and vice versa. A compass needle that once pointed north would, after the event, point south. This isn't speculation. It is a known and recurring feature of our planet's behavior, written into the very rocks beneath our feet. Scientists discovered this history through paleomagnetism. When volcanic lava cools, tiny, iron-rich mineral grains within the rock act like microscopic compass needles. As the rock solidifies, these minerals are frozen in place, aligned with the direction of the Earth's magnetic field at that moment. By sampling and dating lava flows from different eras, scientists have reconstructed a detailed timeline of the magnetic field's history stretching back hundreds of millions of years. And that record is clear. Pole reversals are a normal part of Earth's life cycle. On average, over the last 20 million years, a reversal has occurred every 200,000 to 300,000 years. Here is the interesting part. The last full reversal, the Brunhes-Matayama reversal, happened about 780,000 years ago. By this broad average, we are overdue for the next one. So, what would a reversal actually look like? It would not be an instantaneous switch. It's a long and complex process that could take anywhere from 1,000 to 10,000 years to complete. During this transitional period, the main dipole field, the simple north-south structure we have today, would decay significantly, perhaps to as low as 10% of its current strength. But it wouldn't disappear. Instead, the field would become incredibly complex. The two dominant poles would be replaced by multiple, weaker, local, north and south poles scattered across the globe. The consequences for a technologically dependent civilization would be significant. With the main shield weakened, the planet would be more exposed to solar and cosmic radiation. The auroras, currently confined to the polar regions, could appear almost anywhere on Earth as charged particles follow the tangled magnetic field lines. While beautiful, they would be a reminder of our increased vulnerability. For life that uses the magnetic field for navigation, like migratory birds, sea turtles, and whales, it would be a time of immense confusion. A chaotic, multipolar field could render their internal compasses useless. But the greatest risk would be to our technology. A planet-wide field that is only 10% as strong as normal would mean our satellite infrastructure would be constantly bathed in high levels of radiation. Malfunctions could become commonplace. Our electrical power grids would also be more vulnerable. A powerful solar storm, like the Carrington event of 1859, involves a massive eruption from the Sun called a coronal mass ejection. If a storm of that magnitude were to hit us today, it is estimated it could cause trillions of dollars in damage. Now, imagine a Carrington-class storm hitting the Earth during the peak of a magnetic reversal, when our shield is at its weakest. The induced currents could overwhelm transformers on a continental scale, potentially crippling communication networks. This is the scenario that geophysicists and space weather experts study and prepare for. The future outlook, awareness and preparation. After a journey to the center of the Earth and confronting the possibility of a planetary reversal, it's easy to feel a sense of unease. So, what does this all mean? The overwhelming scientific consensus is that a full geomagnetic reversal is not an immediate threat. These are processes that unfold over geological time, not human lifetimes. A full reversal, should one be starting now, would still likely take thousands of years to complete. Life on Earth has persisted through hundreds of full reversals. It is resilient. A reversal is not an extinction-level event. The more pressing concern is the journey. The ongoing weakening of the magnetic field is happening now. The South Atlantic Anomaly is a present-day challenge for our space-based infrastructure. As the overall field continues to weaken, our vulnerability to space weather grows. We don't need to wait for a full reversal to feel the effects. A weaker shield means a less powerful solar storm could have a much bigger impact in 50 or 100 years. This is not a problem for the distant future. It's a challenge for our generation and the next. This is precisely why the scientific community is so focused on this issue. Missions like the ESA's Swarm constellation are providing the most detailed picture of our magnetic field ever assembled. They are our sentinels in space, tracking every fluctuation and giving us the data needed to model the field's future behavior. By understanding the risks, we can prepare. We can design more radiation-hardened satellites, create smarter power grids, and develop more accurate space weather forecasting to give us advance warning of incoming solar storms. The story of Earth's weakening magnetic field is not a story about the end of the world. It is a humbling reminder that we live on a dynamic and ever-changing planet. We are passengers on a world with a molten heart, protected by an invisible shield that we are only just beginning to truly comprehend. Our survival and the future of our technological civilization depend on our ability to listen to the subtle warnings the planet is giving us, and to act on them with foresight. Our journey took us 3,000 kilometers down into the Earth's churning core, and hundreds of thousands of kilometers out into space. We've seen that our planet's invisible shield is a complex, dynamic, and life-giving force. We've also seen that it is changing, with the South Atlantic Anomaly serving as a quiet reminder of our vulnerabilities, and the wandering poles hinting at a deep, planetary restlessness. The ground beneath our feet feels solid and the sky above looks calm, but we are living on a geological timescale. The planet is reminding us that nothing is permanent, and that in the face of these quiet, immense changes, the greatest shield we have is not just the magnetic field, but our own patient, growing understanding. You have a sixth sense you never knew existed. Imagine, for a moment, an invisible current. A quiet, relentless stream of particles, flowing from the surface of the sun at nearly 1,000,000 miles per hour. This isn't a concept from fiction. This is the solar wind, and it is moving toward us, always. Every day, our planet is bathed in this cosmic radiation. Without a defense, over long stretches of geological time, it would slowly wear away our atmosphere, and leave Earth a quiet, barren rock, much like Mars. But we are not unprotected. Our world is wrapped in a silent, invisible field of force, born from the very center of the Earth. It's called the magnetosphere, and it is one of the things that allows life to exist here. A constant, unseen process that makes our world habitable. This field, however, may do more than just protect us. It's a fundamental force of nature that some life has learned to use. A global network of invisible lines, a map without familiar landmarks. And for centuries we've watched as animals have tapped into it. Every year, the Arctic tern flies from the North Pole to the South Pole and back again, a journey of over 40,000 miles. On moonless nights along the coast of India, tiny sea turtle hatchlings, small enough to fit in your palm, dig their way out of the sand and move unerringly toward the ocean, waters they have never touched, with no parent to guide them. They seem to do it by feeling their way along the invisible lines of the Earth's magnetic field. They are using a hidden sense, a biological ability called magnetoreception, the capacity to perceive the planet's invisible, steady presence. For a long time, it was believed this was a sense reserved for the animal kingdom. That humanity, for all its technology, had somehow never evolved this connection to our world. But what if that assumption was incomplete? What if that sense isn't missing? What if it's just quiet? New evidence suggests that we may have this ability as well. A subconscious, biological inheritance that connects our brains directly to the planet. A sixth sense you may never have known existed. Today, we begin a quiet journey. A path that will take us from the churning core of the Earth, to the unusual physics in a bird's eye, and finally, deep inside the subtle wiring of the human brain. We are going in search of a quiet sense. The invisible heart of the planet. To understand this hidden sense, we first have to understand its source. The story of magnetoreception doesn't begin in the sky or in the ocean. It begins nearly 2,000 miles beneath our feet, at the center of the Earth. Here, in the outer core, is a vast ocean of liquid metal, mostly iron and nickel. The pressure is immense, and the temperature is staggering, hotter than the surface of the sun. This molten metal is in constant motion. As the Earth spins, it drags this metallic sea with it, twisting the flow of liquid iron into enormous, continent-sized columns. And in this constant, planetary motion, something incredible happens. The movement of this conductive fluid generates massive electrical currents, a principle known as electromagnetic induction. These electrical currents, in turn, create their own magnetic field. This field then influences the flow of the iron that created it, which reinforces the electrical currents. This self-sustaining feedback loop is known as the geodynamo. It transforms the Earth's core into a planet-sized electromagnet, a self-powering generator that has been running for billions of years, creating the magnetic field that defines our world. Now, if you're picturing a force of incredible strength, you might be surprised. At the Earth's surface, the magnetic field is actually quite weak, many thousands of times weaker than a common refrigerator magnet. You can't feel it on your skin. Its influence comes not from its strength, but from its sheer scale. Picture the Earth as a large bar magnet, tilted slightly from our planet's spin axis. From the south magnetic pole, invisible lines of force emerge. They loop millions of miles out into space, wrapping around our planet in a vast, protective bubble, before returning at the north magnetic pole. This bubble is the magnetosphere. And it is this bubble that meets the unending flow of the solar wind. As that stream of charged particles from the sun washes over our planet's defenses, the magnetosphere deflects the vast majority, over 99%, of the incoming radiation. It is a cosmic shield, without which our protective ozone layer would be damaged, and harmful radiation would reach the surface. Planets that lost their magnetic field, like Mars, saw their atmospheres slowly stripped away and their surfaces sterilized over eons. On the night side of the Earth, the side facing away from the Sun, the magnetosphere is drawn out into a long tail, called the magnetotail, stretching hundreds of thousands of miles into space. Within this massive, invisible structure are zones of trapped radiation, the Van Allen belts. These are regions where particles from the solar wind spiral along the magnetic field lines, held at bay. They are a quiet reminder of the radiation the magnetosphere protects us from, a region so intense that spacecraft must navigate it carefully to avoid damage to their electronics. For the most part, this entire process is completely invisible. We live and walk through these lines of force every day without any conscious awareness. But sometimes the shield makes itself known. On clear, dark nights at high latitudes, the sky can fill with a silent, shimmering dance of light. The aurora borealis and aurora australis. This is the visible proof of the protection happening far above our heads. When the solar wind is particularly strong, some charged particles can be funneled down the magnetic field lines toward the poles. Then, at altitudes of 60 to 250 miles, they collide with the molecules of our upper atmosphere. When these particles strike oxygen atoms, the sky glows in greens and sometimes reds. When they hit nitrogen, we see blues and purples. The curtains of light you see are a direct visualization of the planet's magnetic field lines, illuminated by energy from the sun. The aurora is the visible evidence of this quiet protection. This is the arena, a planet wrapped in an invisible, life-sustaining field of force. A field that is both a shield and, as we will now see, a map. The animal kingdom's hidden sense. For centuries, naturalists were faced with a quiet mystery. How did animals perform such remarkable feats of navigation? Before satellites, GPS, or even reliable maps, countless species were crisscrossing the globe with quiet accuracy. We've already mentioned the Arctic tern. But the examples are everywhere. Loggerhead sea turtles, after migrating thousands of miles across the open ocean, will return to the very same stretch of beach where they were born. Salmon, after years at sea, find their way back to the exact stream of their birth. Monarch butterflies, with brains no bigger than a pinhead, navigate a multi-generational journey from Canada to a specific forest in Mexico they have never seen. For a long time, we attributed these abilities to other senses. Perhaps they were following coastlines, or smelling their way home, or using the sun and stars. And many animals do use these cues. But these explanations did not seem to cover all cases. Birds could navigate on overcast days. Turtles could find their way across a featureless ocean. And what about animals that live in darkness, like blind mole rats that build complex tunnel systems? There seemed to be something else. Another sense, entirely outside our own experience. The answer, as scientists would discover, was magnetoreception. The ability to sense the Earth's magnetic field. They weren't just following it like a compass pointing north. They were reading subtle variations in the field to create a mental map. They could sense not just polarity, the north-south direction, but also the field's inclination, or the angle at which the field lines dip towards the surface. This dip angle is horizontal at the equator and points straight down at the poles, providing a reliable indicator of latitude. In effect, they were using a biological navigation system, powered by the planet itself. But how? How can a living being detect an invisible force? For decades, this question led to two primary, and very different, theories. The first theory is the magnetite hypothesis. Scientists discovered that many of these animals have microscopic crystals of a mineral called magnetite within their bodies. Magnetite is naturally magnetic. The idea is that these tiny, biological magnets are located inside specialized receptor cells. Like the needle of a compass, these magnetite crystals would physically twist and align themselves with the Earth's magnetic field. This physical movement could then trigger a nerve impulse that is sent to the brain, which would interpret the signal as directional information. In some animals, like the rainbow trout, these magnetite-based receptors have been found in the snout. It's an intuitive, mechanical model, tiny, living compasses connected to the nervous system. For a long time, this was the leading explanation. But a second theory emerged, one that was far less direct, and came from the unfamiliar realm of quantum physics. This is the radical pair mechanism, and it suggests that some animals don't feel the magnetic field, they might actually see it. This theory centers on a class of proteins called cryptochromes. These proteins react to light, and they are found in the retinas of birds, as well as many other plants and animals, including humans. The proposed mechanism is unusual. When a particle of blue light strikes a cryptochrome molecule in a bird's eye, it can create a radical pair, two molecules that become magnetically linked. Their quantum states are intertwined. The weak geomagnetic field can then influence how long these electrons remain in their synchronized state. This, in turn, affects the chemical signals sent from the cell. Depending on the angle between the bird's head and the Earth's magnetic field lines, the chemical signals sent from the retina to the brain will change. The result would be a pattern, or a filter, superimposed over the bird's normal vision. The bird might see the world with a pattern of light and dark that changes as it turns its head. By keeping this pattern aligned in a certain way, the bird can hold a constant bearing. It would literally be seeing the invisible lines of force. This may be why many birds seem to need light to navigate. Their quantum compass might not work in the dark. This isn't just a hypothesis. Researchers have found that a specific cryptochrome thought to be responsible, Cry4, is produced at constant levels in the eyes of migratory birds, suggesting it's used for a constant function like navigation, rather than just keeping time. So we have two very different biological mechanisms. One, a microscopic mechanical compass. The other, a quantum sensor that allows an animal to see invisible forces. For a long time, the question was, which one is right? The answer, it seems, may be both. Different animals appear to use different systems, and some may even use both. The animal kingdom had evolved at least two distinct ways to tap into the planet's quiet presence. And for most of history, we stood on the outside, looking in, assuming we were the one species left out, disconnected from this fundamental force of nature. The consensus was clear. Humans do not have a magnetic sense. But science is a story of revised ideas. And the search to find this ability in ourselves was just beginning. The human connection, the search for our quiet sense. And so we arrive at the central question: what about us? Are we, a species that has mapped the stars and the human genome, truly unaware of the quiet hum of our own planet? For most of the 20th century, the answer from the scientific community was yes. The idea of a human magnetic sense was often considered pseudoscience. The reasoning was simple. If we had such a sense, we would know it. We don't consciously feel magnetic fields, therefore, we can't sense them. But this argument assumes that all senses must be conscious. You are not consciously aware of your brain monitoring your blood pressure, or your inner ear making constant, tiny adjustments to keep you balanced. Your senses are a vast network, and your conscious awareness is only part of their function. What if a magnetic sense was operating entirely below the surface of our perception? The first hints that this might be the case came from a series of experiments in the 1980s by a biologist named Robin Baker. He would put blindfolded students in a van, drive them on a complex route, and then, at a remote location, ask them to point the way back home. The results were surprising. The students often pointed with an accuracy that was better than random chance. Even more strangely, Baker found that if he placed a magnet on the student's head, their accuracy disappeared. The studies made headlines. Had he discovered a human sixth sense? But the excitement did not last. The results proved frustratingly difficult to replicate. Other labs tried similar experiments and got random results. Science requires repeatability, and the human compass phenomenon seemed to fade under further scrutiny. For years, the field went quiet. But a handful of scientists didn't give up. Among them was a geophysicist from Caltech named Joe Kirsch-Vink. He had long suspected that humans were not the exception. He believed the earlier experiments failed not because the sense didn't exist, but because they were too noisy. The modern world is filled with electromagnetic interference. A faint, biological signal would be easily drowned out. Kirsch-Vink knew that if he was going to find this sense, he had to listen in absolute electromagnetic silence. So, he built a special room. A Faraday cage, an enclosure made of aluminum designed to block all external electric and magnetic fields. Inside this shielded box, he placed a set of coils. By running precise electrical currents through these coils, he could create a pure, uniform magnetic field identical to the Earth's, and he could rotate it in any direction he wanted, silently and invisibly. Now, he needed a way to listen to the brain. He turned to electroencephalography, or EEG, which uses a cap of electrodes to record the brain's electrical activity. He was looking for a change in one particular type of brainwave, the alpha wave. Alpha waves are dominant when your brain is in a relaxed, idle state. But when your brain detects a new stimulus, a sound, a light, a touch, and shifts to process it, the alpha waves decrease. This drop is a reliable, hardwired signature of a brain processing sensory input. The experiment was simple. A participant would sit in total darkness and silence inside the chamber. For an hour, Kirsch-Vink would silently rotate the magnetic field around them, while the EEG recorded their brain activity. The participants felt nothing, but their brains told a different story. When the data was analyzed, a clear pattern emerged. As the magnetic field rotated, there was a sharp, significant drop in the participants' alpha waves. This was the classic signature of a brain detecting and processing a signal. The brain was responding. Without any conscious awareness, a set of neurons was firing in response to the silent rotation of a magnetic field. But there was another detail, one that made the finding even more compelling. The response only happened for certain rotations. The experiment was conducted in the northern hemisphere, where the Earth's magnetic field lines dipped downwards. The brain only reacted when the artificial field was rotated in a way that mimicked this downward-pointing field. When Kirsch-Vink programmed the coils to create an upward-pointing field, the kind found in the southern hemisphere, the brain showed no response. This was critical. It meant the brain wasn't just reacting to any change, it was selectively processing information. This was not a simple physical artifact. It appeared to be a biological response. In 2019, Kirsch-Vink and his colleagues published their findings. After decades of doubt, here was the first robust, replicable, neuroscientific evidence for a human magnetic sense. The discovery was a landmark, but it opened a deeper mystery. If our brains are processing magnetic information, how are they detecting it? Where are the sensors? The search for the human sensor brings us back to the two theories from the animal kingdom. And the evidence suggests that we, humans, may possess the biological machinery for both. First, magnetite. In 1992, Joe Kirsch-Vink's team made a discovery. They found tiny crystals of biogenic magnetite inside human brain tissue. These were the same kind of structured crystals found in magnetotactic bacteria. They are most highly concentrated in the cerebellum and the brainstem, older parts of the brain responsible for motor control and processing sensory input. The raw material for a magnetite-based sensor seems to be there. Now, what about the quantum compass, the cryptochrome proteins? Humans have cryptochromes in our retinas, where they help regulate our internal clock. But could they also sense magnetism? To test this, scientists performed an ingenious experiment. They took fruit flies, which have a magnetic sense that depends on their own cryptochrome, and genetically engineered them to lack the protein. These flies lost their ability to navigate. But then, the researchers inserted the gene for human cryptochrome into the flies. The result was astonishing. The fly's magnetic sense was restored. A protein from a human eye was able to function as a magnetosensor inside a fly. The study demonstrated that human cryptochrome has the fundamental molecular capability to function as a light-sensitive magnetosensor. This did not prove humans use it this way, but it showed that a key component for a quantum compass exists within our own biology. The implications are quiet but staggering. We have the biological components for not one, but two potential magnetic sensory systems. The wiring appears to exist. We may not be as separate from our world as we thought. Our journey began with an invisible shield, a field of force generated by the heart of our planet. We saw how that shield is not just a defense, but a guide. A planetary map of invisible lines that the animal kingdom has learned to read with quiet precision. For so long, we believed we were outsiders to this world. A species so reliant on sight and sound that we had become unaware of the more subtle forces of nature. We looked at the journeys of birds and turtles with a sense of wonder, as if they were performing something beyond our reach. But the story of science often reveals that the mechanisms behind such things are even more wonderful. The search for the human magnetic sense suggests that the connection isn't something external. The components for it may exist within our own biology. The discovery that our brains can subconsciously react to the Earth's magnetic field, the finding of magnetite crystals in our neural tissues, and the revelation that our own retinal proteins have the capability to detect magnetic forces. All of this points to a quiet and profound possibility. We may not be disconnected. The hardware may be there. The link between our biology and the planet's geophysics appears to be real. What does this mean for us? It may mean that an uncanny sense of direction is not just an anecdote. It could be a hint of a biological system working more effectively in some than in others. It reframes our relationship with the natural world, suggesting that our separation from it is an illusion, a product of a modern environment that has simply drowned out a very quiet signal. This isn't a story about a superpower. It is something deeper. It's the discovery of another layer of our own reality. A hidden sense that may have been working in the dark, beneath our awareness, for our entire evolutionary history. It reminds us that there are still fundamental discoveries to be made about what it means to be human. The Earth's magnetic field is not just something around you. It may, in a very real way, be something your biology is prepared to sense. A dormant ability, a quiet inheritance. The next time you stand outside on a clear night, far from the city, and feel the ground beneath your feet, perhaps take a moment and wonder. Wonder if some ancient, silent part of your brain is feeling it too. A subtle pull, a quiet resonance, a sixth sense connecting you to the invisible heart of home. If this journey into the quiet senses of our world helped you see things in a new way, consider liking the video and subscribing to the channel. We spend a lot of time exploring these topics, and your support makes it possible. And feel free to share in the comments below. Have you ever experienced a moment of direction that felt intuitive, something you couldn't quite explain? Let's discuss this hidden human potential. What if Earth's magnetic field disappeared for 24 hours? We exist on this planet, held here by forces we cannot see or feel. Among them is a silent guardian, a planetary shield that has protected life on Earth for billions of years. It is called the magnetosphere, and without it, life as we know it would not be here. This shield is generated deep within our planet, a product of a liquid iron core spinning at immense speeds. It extends tens of thousands of kilometers into space, a bubble that deflects a constant storm of particles fired from the sun. But the shield is not invincible. It weakens and fluctuates. Scientists have observed that its strength has decreased by nearly 9% over the last 2 centuries, and there are areas, like the South Atlantic Anomaly, where it is already unusually weak. This is a real, measured phenomenon. It does not suggest a sudden collapse is coming, but it does invite a question. What if the unthinkable happened? What if, for one full rotation of the Earth, this shield simply vanished? Not a slow weakening, not a gradual flip of the poles, but a complete shutdown for 24 hours. This is a thought experiment. It is a journey through a hypothetical day, exploring the cascading consequences, not to cause alarm, but to understand the importance of something we can never see. From the first subtle signs that something is wrong, to the technological collapse, and finally, to the direct assault on life itself. This story is a quiet reminder of our planet's delicate balance. If this kind of calm exploration into our world helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The science of our planetary shield. Before we begin this journey, it's important to understand what this shield is and how it works. Think of the Earth as a giant bar magnet. This is not just an analogy. Our planet behaves like one, creating a magnetic field that loops from pole to pole and far out into space. But unlike a simple magnet, this field is not static. It is dynamically generated by a process known as the geodynamo. Nearly 3,000 kilometers beneath our feet lies the Earth's outer core, a vast ocean of molten iron and nickel. This liquid metal is in constant motion, driven by convection. Hotter material rises, cools, and then sinks again. The spin of our planet twists these convection currents into massive, spiraling columns. This organized motion of molten metal, an excellent electrical conductor, generates powerful electrical currents. And where there are electrical currents, there is a magnetic field. This is the geodynamo, a self-sustaining planetary engine that creates the magnetosphere. This magnetosphere is not a perfect sphere. It is a dynamic, comet-shaped structure, constantly being molded by the solar wind. The Sun constantly ejects a stream of charged particles that travels through space at immense speeds. On the side of the Earth facing the Sun, the magnetosphere is compressed. On the night side, it's stretched out into a long tail. This structure is our primary defense. When charged particles arrive, our magnetic field deflects the vast majority of them, forcing them to flow around the planet like water around the bow of a ship. Without this deflection, the solar wind would directly impact our atmosphere, stripping it away over time. This is the process that scientists believe turned Mars from a world with a thick atmosphere into the cold, barren desert it is today. There is another component to this shield. Within the magnetosphere are 2 donut-shaped zones of trapped radiation known as the Van Allen belts. They capture high-energy particles, holding them in a spiral around the planet. They are a secondary buffer, preventing the most energetic particles from reaching us. The disappearance of the magnetic field means not just the loss of the deflector shield, but also the release of the radiation already trapped within these belts. With this understanding of our silent protector, we can now begin our clock on a day without it. The first hour, the unraveling begins. The moment the magnetic field vanishes, there is no grand explosion, no earth-shattering sound. For most people going about their morning, nothing seems immediately different. But for those who know what to look for, The signs are immediate and deeply unsettling. The first casualty is navigation. Every single magnetic compass becomes useless. The magnetized needle, which for centuries has reliably pointed north, now spins erratically or simply aligns with any nearby piece of metal. For hikers, for sailors on the open ocean, it's the first sign that the world is not working as it should. In an instant, they are lost. A far greater and more immediate problem is unfolding in the animal kingdom. Many creatures rely on an internal sense of magnetoreception for migration and orientation. Migratory birds suddenly find their internal compass gone. Flights that were perfectly navigating a moment before become disoriented masses. They might fly in circles or veer off course by thousands of miles. The oceans are no safer. Sea turtles, known to navigate vast oceanic basins to return to the beaches where they were born, are now adrift. Whales, which follow magnetic highways, find themselves in an alien world. Mass stranding events would likely occur as entire pods, lost and confused, swim into shallow waters. Even honeybees, which use the magnetic field to help navigate back to their hives, would get lost, threatening pollination for countless plants. For humanity, the first hour brings more subtle technological omens. In areas with long transmission lines, especially at higher latitudes, the first trickles of unshielded solar wind particles begin to induce weak, unstable currents on the grid. Lights might dim for a moment. Sensitive scientific equipment would be blaring alarms in empty labs, their readings flatlining to zero. Satellites in low Earth orbit begin to experience glitches, particularly those passing through the region we call the South Atlantic Anomaly, a spot where the field is already naturally weaker. A communications satellite might experience a burst of static. The GPS network begins to accumulate errors. Your phone's map might show you a block away from your actual location. These are the first tremors of the technological earthquake to come. The invisible framework that supports our world is gone, and the systems built upon it are beginning to fray. The sixth hour, the great blackout and the silent sky. 6 hours in, the subtle fraying has become a catastrophic failure. The planet is now fully exposed to the unfiltered solar wind. This stream of charged particles, no longer deflected, slams directly into the upper atmosphere. This interaction triggers a chain reaction that brings our modern civilization to a halt. The primary mechanism is something called geomagnetically induced currents, or GICs. As solar particles interact with the Earth and its ionosphere, they induce powerful, low-frequency electrical currents in the planet's crust. These currents seek the path of least resistance, which humanity has conveniently provided: our power grids. Long-distance transmission lines act like giant antennas, soaking up these currents. The problem is that our grid is built for alternating current, AC, while GICs behave more like direct current, DC. When this DC-like current flows into the massive transformers at electrical substations, it causes them to saturate and rapidly overheat. Their magnetic cores are pushed beyond their limits. The result is a domino effect on a planetary scale. It begins at higher latitudes. In places like Canada and Scandinavia, massive transformers begin to fail. Some trip their safety relays. Others physically melt down or explode. The 1989 Quebec blackout, caused by a relatively strong but not unusual solar storm, plunged 6 million people into darkness. That event was caused by a storm interacting with our shield. This is happening with the shield completely gone. Within this 1 hour, a cascading failure ripples across the globe. As one section of the grid fails, it puts an unmanageable strain on its neighbors. North America goes dark, then Europe, then Asia. Within hours, virtually every major power grid on the planet is offline. The world is plunged into an unprecedented blackout. There is no light, no heating, no air conditioning. Water pumps stop. Fuel pumps are useless. The entire cold chain of food and medicine preservation ceases. The disaster isn't just on the ground. Satellites are now flying through a firestorm of radiation. Without the magnetic field's protection, their sensitive electronics are bombarded by high-energy particles. Solar panels degrade. Onboard computers suffer short circuits. Memory chips are scrambled. The GPS constellation goes silent, one satellite at a time. The fleet of communication satellites that relay internet data, television broadcasts, and phone calls are fried. The world is not only dark, but also silent. Weather satellites are blinded. The sky, once filled with invisible data, is now becoming a graveyard. Thousands of dead satellites begin to tumble. Their orbits will slowly decay. The silent, dark sky above is now littered with the husks of our technological age, waiting to become a terrifying meteor shower in the weeks and months to come. The modern world has effectively ended in just 6 hours. The 12th hour, a beautiful and terrible dawn. As the Earth continues its rotation, half the planet is now in a darkness deeper than any modern human has experienced. The familiar glow of cities is gone. But this darkness is about to be replaced by a light of breathtaking beauty and profound horror. All over the world, the sky begins to shimmer. These are the auroras. Normally confined to the polar regions, they are a side effect of the magnetic field funneling solar particles toward the poles. But without the magnetic field to guide them, the particles are now raining down everywhere. The spectacle is global. Over the Sahara, ghostly green sheets of light ripple across the sky. Above the silent skyscrapers of Tokyo, vibrant curtains of red and purple pulse with an unnatural energy. The entire planet is wrapped in an aurora so bright it is said one could read a newspaper by its light. The colors tell a story of the atmosphere's assault. The most common green is from particles striking oxygen at altitudes of 100 to 300 kilometers. The rarer reds are from oxygen at even higher altitudes. The purples and blues are from interactions with nitrogen. This light show is the visual evidence of our atmosphere being bombarded. And this radiation is the true threat. For the first 12 hours, the Earth's atmosphere has provided a substantial shield, as effective as a thick wall of concrete. But it cannot stop everything. 2 types of radiation are now pouring in. The first is from the solar wind itself, a flood of solar energetic particles, SEPs. The second, and more dangerous, is galactic cosmic rays, GCRs, high-energy remnants of distant supernovae that are normally deflected. Anyone in a high-altitude airplane when the field disappeared would receive an immense radiation dose, comparable to hundreds of chest X-rays. Symptoms of acute radiation sickness would begin. On the ground, the effect is more insidious. Radiation levels climb steadily. High-energy particles streak through the bodies of every living thing, acting like microscopic bullets, shredding DNA. Our bodies have mechanisms to repair this damage, but they are quickly overwhelmed. The sun, the source of life, is now an object of menace. With the ozone layer also beginning to be affected, harmful ultraviolet, UV, radiation at the surface is on the rise. The beautiful, terrible auroras are a warning. The sky is no longer a shield, it is a battleground. The planet is being bathed in a lethal glow, and the very fabric of life is beginning to degrade. The 24th hour, on the precipice. After a full day without its magnetic shield, the Earth is on the brink of a biological catastrophe. The immediate technological collapse was just the prelude. The true crisis is the relentless, invisible assault of radiation and the beginning of the planet's slow, physical dismantling. The radiation dose received by every person on the surface is now critical, high enough to induce symptoms of acute radiation syndrome, ARS, in a significant portion of the population. People would begin to experience persistent nausea, headaches, and fatigue. The DNA of every living thing has been damaged on a massive scale, a ticking time bomb of future cancers and genetic mutations. But an even more existential threat has now begun. The solar wind is not just radiating our planet, it is actively tearing it apart, molecule by molecule. This process is called atmospheric stripping. High-energy particles from the solar wind slam into atoms in our upper atmosphere. A gas molecule, like nitrogen or oxygen, can be hit with such force that it is accelerated beyond Earth's escape velocity. It is knocked out of the atmosphere and into space, lost forever. This is the process that stripped Mars of its once thick atmosphere after its own magnetic field died. While the complete erosion of Earth's atmosphere would take millions of years, the process begins immediately. After just 24 hours, there would be a measurable drop in atmospheric density at the highest altitudes. The air we breathe is being physically sandblasted into the void. This has a direct consequence for our planet's water. As atmospheric pressure decreases, the boiling point of water drops. The process would begin at high altitudes. Water vapor in the upper atmosphere would be broken down by UV radiation and stripped away into space. The planet is beginning to lose not just its air, but its water. The psychological toll of this day is immense. Humanity, stripped of its technology, is reduced to a state of primitive fear, staring at a beautiful sky that is killing us. The 24-hour mark is not an end, but a transition. It is the moment we cross the threshold from a short-term catastrophe to the beginning of a long, slow planetary death. The aftermath and the nightmare scenario. And then, as abruptly as it vanished, it returns. The geodynamo sputters back to life, and the magnetic field snaps back into place. The invisible shield is restored. The solar wind is deflected. The 24-hour nightmare is over. But the world it leaves behind is broken. The immediate aftermath is a struggle for survival in a world reset to a pre-industrial age. Trillions of dollars of infrastructure have been wiped out. The power grids are destroyed. The massive, custom-built transformers have been fried. To replace them on a global scale would be the work of decades, assuming a society could even organize such a feat. The sky itself has become a source of unpredictable danger. The orbits of thousands of dead satellites are decaying. In the weeks and months that follow, the sky would be filled with an almost constant meteor shower as this debris burns up. Some larger pieces would survive re-entry, leading to unpredictable impacts. The most profound damage is biological. In the years that follow, cancer rates would skyrocket. The genetic integrity of our species, and countless others, would be compromised. The psychological scar of that one day would haunt our culture for millennia. But this is the optimistic scenario. This is the world where the shield came back. Now, we must confront the true nightmare. What if it didn't? What if the shutdown was the permanent death of the geodynamo? In this scenario, there is no recovery. The processes that began on that first day would continue, unabated. The atmospheric stripping would never stop. Over thousands of years, the air would thin until it became unbreathable. As the pressure fell, the oceans would begin to boil away, not from heat, but from the lack of pressure holding them in their liquid state. The Earth would be shrouded in a thick cloud of its own evaporating water, but this water would be relentlessly stripped away as well. The surface would be completely sterilized by radiation. Any survivors would be forced to live deep underground, becoming a species that could never again look upon the sun. Over millions of years, the Earth would follow the path of Mars. Its oceans would vanish. Its atmosphere would become a thin whisper of what it once was. The blue marble would become a red, dead rock, a ghost planet. This is the ultimate consequence, a reminder that our existence hinges on the violent, churning heart of our planet, a force that, for 24 hours, we imagined had stopped. From a spinning compass to a silent world, from a global aurora to the air itself being stripped into space, the disappearance of Earth's magnetic field for just 24 hours would represent one of the greatest imaginable catastrophes. It would be a disaster in layers, first dismantling our technology, then our bodies, and finally, the planet itself. This thought experiment, while extreme, is grounded in real science. It underscores the profound importance of a planetary feature we can never see. Our magnetic field is not just a scientific curiosity, it is the silent, unsung hero of life on Earth. It is the reason we have air to breathe and water to drink. The current weakening of the field is a real phenomenon that scientists are studying. While a 24-hour shutdown is not a scenario they predict, it serves as a powerful reminder of the delicate balance that makes our planet a habitable sanctuary in a violent universe. Could humanity survive? Perhaps. But the world we would inherit would be a shadow of its former self, a testament to the day the shield fell, and the sky came crashing down. Thank you for watching.